will present our. Can you hear me? Yes. Okay, where experts from different fields will present the challenges and solutions of combining high modular, high energy, and high power batteries, novel converter concepts, and also production technology solutions derived from the automotive sector. I'm Marguiña Lacano, a researcher and lecturer at Mondragon University. I will try to guide you during the day. We are so glad to host this event, both for people present here and also for those attending online. And we hope everyone enjoys the day. Okay, thank you. And we would like to inform you that this workshop will be recorded and then will be available also on the Seabat project website. Okay. Here we have today's program. We had a small change. And as you can see, we have a variety of presentations on different topics related to battery systems, converters, etc. As this academic workshop is part of the Seabat project, we will start with a brief introduction to the project. Then we will continue with an overview of the solutions and challenges that we have in this sector. We will also talk about different ways to design the modular and flexible battery system. And also will give some considerations regarding the integration of these solutions. We hope to finish the workshop more or less at 4, maybe a little bit earlier, and then we'll have a tour through our labs and facilities. Okay, so let's start with the first presentation, the introduction to the Seabat project. That will be done by my colleague Jeroen Stutz from Flanders Make. Jeroen was born in 1990 in Belgium. He holds a PhD degree in electrical engineering from University of Leuven in Belgium, as well as a Master of Science degree in energy engineering. During his PhD, he co-founded a project on energy education for children called Lumen. And in 2018, Dr. Stutz joined Flanders Make as a research engineer, and in 2021 became core lab manager of the Motionless Core Lab. Dr. Stutz is still an active researcher with his primary interest in electrical energy, power electronics, and drives. And in that context, he leads a project on DC grids in industry and is project coordinator of the Seabat project. So please, Jeroen, over to you.
Good morning, everyone. Also on my behalf, a warm welcome to this first physical event of our Seabat project. It warms my heart to see everybody in person instead of on Teams. I also welcome everybody still attending on Teams. I cannot see you, but I believe you can see me. So also an online welcome still. These hybrid events are here to stay, and it's all about hybrid today anyway, so it's a very good match. As soon as we figure out how to start the presentation, I will give you a brief introduction to the Seabat project to set the scene a bit, but the real technical content is here to be presented by the colleagues of the project, to which I look forward myself as well. I will start with the generic introduction of Seabat, which is really a 4-year project funded by the European Commission under the Horizon 2020 project, or the Horizon 2020 system. It takes 4 years. We're somewhere in the middle. And so we started the 1st of January 2020. So almost 1.5 years ago. And there are 15 partners from 8 different countries, many of which are presented here today. Let's see if this works already. Yes, perfect. And we have a budget of around 10 million euros, so that should be enough to do something decent in the world of the maritime batteries. So why are we doing this? Well, basically to make the world a better place, to start very high level, we want to work towards decarbonization. We want to get these fossil fuels, or at least the CO2 emissions, out of our world. That's clear for everyone, I think. And the International Maritime Organization translated that into a 50% reduction of greenhouse gases somewhere in the near future. And that means that at least for some parts of the maritime industry, we should evolve towards full electric ships. We could do that by using batteries. Current technology is mainly using one type of battery in your ship, something which can hold a lot of energy, because these trips require a lot of energy. So that's what we call a monotype battery. And typically for shipping, for maritime industry, the production is quite scattered. It's a bespoke design for a specific ship, which makes it very expensive, sometimes, or most probably a bit oversized. And if we look at the current research on batteries, it's mostly related to the automotive industry, where we are pushing a lot on these battery electric vehicles. But of course, that research is targeting automotive applications, which is not necessarily the same. It's pushing for better performance and a competitive price. But if you combine that research with the existing technology in the maritime industry, we have an inflexible and non-optimized design when you consider the maritime application, which is what we're interested in today. So as mentioned, this inflexible design gives you typically an oversized capacity of your battery inside your ship, gives you a high cost, a high weight, and a large volume, which of course is counterproductive for the economic working of a ship. And in Seabat, we tried to do something new. We go towards hybrid events, hybrid batteries. Let's try that as well. Let's try and combine different types of battery. For example, NMC cells, LTO cells, supercapacitors, what have you not. Different types of battery cells to optimize the sizing for each ship type. And we do it in a modular fashion. We use preset packages of batteries such that you can combine them for your application. Try to make it as standard as possible and try to mix it with the production technology that we have researched already in the context of the automotive industry. And that should lead towards an oversizing which is much closer to the requested capacity. Still needs some oversizing for aging, for example, but it should also drastically reduce the cost and reduce the weight and the volume, ideally. So our target in this project is to develop a full electric maritime hybrid battery concept. That's quite a mouthful. Full electric, because we are really targeting a full electric ship, albeit that this concept, this hybrid battery concept, can also be used in hybrid ships, where we can combine electric propulsion with something differently. And the hybrid concept, hybrid battery concept, thus means combining different battery technologies. That's a very important concept throughout this day. We modularly combine them. I already mentioned that. We need new power electronic converters to be able to achieve that. So that's something you will learn about today as well. You cannot just connect the terminals of two completely different battery cells. You need something to control everything in the middle. And we will try to use the production technologies from the automotive sector to also improve the standardization of production capacity in the maritime sector. How are we going to do that? Well, first, we start with a proper analysis of what is actually required in the maritime sector. That's also where we will start today in the presentations. What do we actually need? Where is the market going? What is relevant? Then we develop a few full electric hybrid topologies, a few hybrid concepts to trade them off to see which concept, which combination of converters, battery cells, and so on is optimal for a specific design. And we trade off all these elements: cost, flexibility, scalability, the opportunity for fast charging, and so on. And then finally, within the context of this project, we're going to build it. We're going to make a 300 kilowatt hour system to keep the costs also in the project under control. And we're going to virtually validate it for powers and energy capacities of well beyond 1 megawatt hour, which should be sufficient to get it started in the maritime industry. That's only the first step. If we have these, then we have a validated solution for batteries of over 1 megawatt hour for the maritime transport, for waterborne transport. We will work towards a roadmap for type approval so we can get this really installed in industry. And we will take steps towards standardization because it will dramatically improve the costs as well, get everything under control. So that's what we're working towards. As mentioned, we have a consortium of 15 partners spread around Europe. Today we are at the bottom of our consortium physically. So we had a lot of interesting travels. And in our consortium, we have a lot of interesting companies where we try to capture the entire value chain. So we have research institutes and companies really focused on the design and the optimization of power electronics, energy storage systems, and the control to make all of these things work, such as my own institute, Flanders Make, but also ABE, Ikerlaan, where we are here today, and Mondragon University, very specialized in those things. Fraunhofer is taking up the role of the design and development of reliable, cost-effective components and safety. Imekar, our partner from Turkey, is here to produce the battery packs as an expert in that field. SEA, who is excused today, is our testing facility. They can test all these things. We have a lot of end users in our consortium, which is really interesting to really get a hold of the maritime industry, to get them as closely involved as possible. So we have representatives here from Damen, Fincantieri, Vart, and Surmar, who is representing a lot of different shipyards. I'm very happy to have those on board. We have research institutes and companies involved for research and technology transfer, technology qualification, also very interesting towards especially the end of the project to get it as close to the market as possible. And then today online, the project management, dissemination, and exploitation uni research is also part of this project. And that gives us the entire value chain. It gives us a lot of different viewpoints to get our solution as close to reality as possible and to get it spread out so that we can really try and make this happen in real life. But there is a last bullet still hidden on this slide, and that is the stakeholder group. So within Seabat, we have invested a lot on involving as many parties as possible. So we have a stakeholder group of many other institutes and companies, and it's still open for you to join. So we try to involve everybody as closely as possible to this project. One of the members of the stakeholder group is also our sister project, Current Direct, from whom you will see a presentation later today. So we're also not tackling these questions alone. And with that, I am done with the introduction of this set, and let's dive into the details. If you want to review this later on, or if you want to have a look at our deliverables, the public deliverables, the things we have done so far, feel free to visit our website. There you will be able to find everything of this workshop and what we have done so far. And with that, I'm glad to give the word back to Arginie, who will introduce the next speaker, the first real technical content for you today. So I hope you enjoy the event a lot, and let's talk to each other later on during the breaks, poster sessions, and so on. Have fun, everyone.
Okay. So our next speaker is Fabio Mandrile from Polito. Fabio received the Master of Science and PhD degrees in Electrical Engineering from Politecnico di Torino in 2017 and 2021, respectively. He's currently assistant professor at Dipartimento Energia Galileo Ferraris at Polito, and his main research interests are virtual synchronous machines and power electronics for grid-connected applications, on which he focused his PhD and current research activity. So Fabio, the floor is yours.
Thank you very much.
To pass the slides, you have to go.
Okay, there is also the laser. Okay, thanks. Okay. Okay. Okay, we are waiting for the slides. While we are waiting, Hello everyone, or egun on, as they say here in the Basque countries. I'm Fabio Mandrile. Thanks Argine for the presentation. I'm from Politecnico di Torino. I will show you a couple of pictures of the city, also because next workshop next year will take place there. So it's good that you know something about it. Okay, thanks. My presentation will be a general introduction on the topic of battery sources and power converter interfaces for waterborne transportation application. So, as I promised, as I promised, here are some pictures. Torino is located in the northwest of Italy, here close to France. And here you can see a picture, well, of my university and of the city of Torino. The nice thing about our city is that we are very close to the mountains, so you can enjoy a very beautiful view. We are famous for, well, football. I hope you know Juventus football team. Cristiano Ronaldo recently left us. Then we are famous for Fiat cars. Fiat was born and founded in Torino. And we are famous for this building, which is called Mola Antonelliana, which is our city symbol, and from which you can enjoy a wonderful view on the city and on the mountains. So you will be welcome to join us next year. In Politecnico di Torino, I am also part of this research group called the Power Electronics Innovation Center, or PEIC. We are a research group focusing on power electronics, the power electronics chain from send to the application. There are several departments involved, from the more micro technologies guys up to us. I'm focusing on the last part of this chain. So power converters and application of these converters to the final systems. So for example, energy or transportation. And we are quite a large group because we have more than 40 members comprising professors, researchers, and PhD students. Going into the topic of today, we will talk about the electrification of the maritime propulsion systems. A key aspect of these, to enable these, are the storage systems. So we can think of several types of storage systems. Battery is the topic we are focusing on today, but there will be also, for example, fuel cells. So the question is now, how do we arrange these storage systems and the converter, the power electronics interface to the rest of the shipboard grid? And also, how do we optimize internally these battery storage systems? So for example, with a hybrid storage system with high energy and high power battery technologies. About this, we have several battery technologies. As you probably know, we can start from the lead acid batteries, which you will all have in your cars, I guess. But then we can shift also to lithium-ion batteries, lithium technologies, which you might also have in your car if you have an electric car or a hybrid car. So the idea here is to exploit different chemistries and different technologies to create these hybrid battery packs composed of a high power technology, can also be something else apart from batteries. For example, supercapacitors. In this project, we will use, let's say, high power batteries. And a second part, which is a high energy battery. Okay. In the next presentation, you will see more details about this. The idea behind this hybrid energy storage is, let's say, a very simple concept. If we have, for example, a very simple load profile on our ship, like this one, we can say, okay, we need a certain peak power and we need a certain total energy, which is the integral, the area of this power profile, and a certain number of cycles over, I don't know, a day or a year or whatever. The idea is, okay, let's try to optimize, minimize the cost of this battery pack. So instead of obtaining the power and the energy with a single technology, which must be capable of providing both at the same time, why don't we reach the same goal with, for example, two different parts? So one which focuses more on energy and one which has a higher peak power, okay? To do this, there is a lot of optimization behind it, and my colleagues will tell you something about this. We cannot forget about power converters, because batteries alone cannot be interfaced to a shipboard system. So we have also some requirements for the converters. First off, we need bidirectional converters, because we must be able to charge and discharge these batteries. Then often we need isolation from the batteries to the rest of the system, and this can be done either at converter level or in the shipboard distribution grid. Then, of course, we need high efficiency in our converters, because we don't want to waste energy just for converting it to the end applications. We also want small and lightweight converters, because on a ship, every cubic meter and every kilograms has a cost. So this is also a factor of cost. And also we want control techniques for these converters, which can optimize the exploitation of the batteries to increase their lifetime. As Jerome said before, we have a standard solution now, which is basically a monotype battery, so a single technology, directly interfaced to a power port in DC. But this has the advantage that this DC voltage varies with the state of charge of the battery. So therefore, any converter which is connected here must be able to deal with this voltage range. So we might have an oversizing of all the converters behind this power port. A second opportunity we might think of is to place a DC-DC converter between the monotype battery and the DC output. Therefore, we can regulate this output voltage, therefore avoiding the oversizing of the converters in the rest of the network. But the question is, can we do better? And the answer is yes. This is what we are trying to do here in this project. For example, we can think of a so-called semi-active structure for hybrid storage systems. In this structure, we directly connect a battery technology to the output. It can be either high power or a high energy technology. And we connect another technology through a DC-DC converter. In this case, we can obtain, let's say, exploit differently these two batteries according to the operating point. However, since we connect directly a battery at the output, we have the disadvantage of a variable DC voltage output, depending on its state of charge. Therefore, it could be interesting to shift to a full active structure for these hybrid storage systems. So each and every storage technology has a dedicated DC-DC converter to manage the power flow. Therefore, we have the advantage of a regulated DC output, and also we can optimize the exploitation of these batteries. However, this comes to the cost of a higher complexity. Of course, we have more power electronics to deal with. Another possible solution, and here I think the colleagues here at Mondragon are the experts, is the so-called partial power processing. So we can think of a converter structure which only works on a fraction of the power of the system. So instead of sizing a full power converter, we let most of the power directly flow from the battery to the output, and we only regulate a part of this power. Therefore, we can have much better efficiency, so because we have less losses, and also we can have potentially savings in terms of weight and complexity. However, this for sure, let's say, forbids us from providing galvanic insulation inside the DC-DC converter system. In conclusion, well, the maritime electrification is a growing business, so there is a lot of interest nowadays in this sector. However, the question of how do we integrate and use the storage inside these vessels is still an open topic, and that's what are we trying to study here. An appealing solution are these hybrid storage systems with different battery technologies. However, we have to develop optimization solutions for these battery packs and converters. So there is a lot of study necessary behind this, and in the next presentation, my colleagues will tell you something more in detail about this. This is all from my side. Thank you very much for your attention, and if there is any question, please ask.
Is there any question? We are a little ahead of schedule, so you have time.
Also, if you want any question about Torino, I don't know, typical food and such, it's fine.
Okay. So, thank you, Fabio.
Thank you.
Okay, so our next speaker is Andrea Colavito. Andrea joined Fincantieri Group in October 2020, and he achieved a PhD in industrial engineering at the University of Trieste a few months later, with a thesis on methods and tools for the design of naval and marine power systems. He's now operating as Head of Research and Innovation at Fincantieri SI, providing innovative solutions to reach the decarbonization of both the maritime and the industrial sectors. So, Andrea, the floor is yours.
Okay, thank you for the kind introduction, and it's a beautiful moment to be here without any more Teams call. I want to underline this. It's beautiful to see my face. And so I will present the waterborne transport market needs and regulations, which is the output of the first work package of the Seabat project. And the work has been done in the first 6 months of the Seabat project. And I will give you a brief overview of the work package one, of the work that has been done in the work package one, and then going into detailed results of each of the 4 deliverables of the work package one. So the work package one market needs and regulations focus on the real market projection and economic aspects linked to the battery system for shipboard power system, and on the analysis of the regulation and for the reduction of the emissions and on the effect they have on the market of energy storage systems. Of course, this will result in a roadmap of battery production and cost targets, taking into account circular economy in Europe. As my colleagues underlined before, the goals are to understand what are the real market projections on the emission reduction and what are the economic aspects linked to the battery system for ships. We definitely know that the economic aspect is one of the main important in reach the decarbonization. And other goal is to investigate what are the current rules and regulation and what are the modification of the rules in the following years that will be applied and how this will affect the ship owner choices is a really important point. Of course, this will be carried out by analyzing the rules, European and international regulations, as my colleague later on will be explained in detail. And this is due to understand which are the challenges and requirements in the horizon of 5, 10, and 15 years. So I will start with this review of the actual emission from the maritime sector, defining the contribution of different type of ships. Here we have the HFO equivalent fuel consumption in thousands of tons, updated at 2018, split by main engine, auxiliary engine, and boiler. And here we can see bigger the ship, bigger the impact on the equivalent fuel consumption, of course. And this is the starting point of the analysis. We want to reduce this impact on the specific fuel oil consumption. Of course, in the work package 1, deliverable 1, we started from analysis the IMO actions to reduce the greenhouse gases emissions and the solutions to reach in 2050 the zero emissions in the maritime sectors. Of course, there are different solutions to reach the goal, and definitely battery energy storage system is part of the solution of this problem. So we start also from the analysis of the ships that are already equipped with batteries and on the ships that are in order. And these data on the upper part are from 2 different datasets with provision up to 2029. And in the graph here, we have the number of ships in order from 2021 to 2025 divided by types of ships. And we have a higher number of ships that would be passenger ships and ferries. Here, there is also an overview of the ships currently in operations, project developed in the previous years. And of course, here we want to stress that the battery system to be correctly integrated in the ship power system needs definitely power electronics. So that's the reason why in the Seabat project we want to merge these 2 components in one, let me say, to reduce further the size, the weight, and the cost of these components. These are also in the deliverable 2, a trend analysis based on data from currently in operation ships. And the battery capacity installed on board is given here. You see a trend in increase by years. And this is mainly due to these reasons. The price of the energy storage system is decreasing. And the battery energy storage system performance are getting higher with small footprints and reduced weight. So enable higher installation on board ships. Here we have also a figure underline the hybrid ship's length over the year with energy storage system installed. So we can see that over the years, we start from small ships with energy storage systems. Then we are going up higher to 300-meter ships with the energy storage system installed. Why we installed the energy storage system in very long and big ships? For sure, we cannot have full electric battery-powered ships, but energy storage system can improve the overall performance of the ship and the efficiency, the maneuverability, providing also backup function and blackout preventions. This is something that the ship owner wants to have when installing these kind of energy storage systems. So after analysis of different ships and applications, we found a great variability in the capacity of the batteries on board, and demonstrating the importance to have a modular and expandable system, because different ships has different needs. And for the analysis, the market was divided according to the size of the batteries and analyzed in 3 different scenarios. So we have the first scenario when we consider installation of 100 to 1000 kilowatt hours battery system, mainly for hybrid application for small vessels. Then we have another scenario from 1,000 kilowatt hour to 3,000 kilowatt hour. Here we have hybrid application for large ships and full battery propulsion for small ships. And then we have another scenario with more than 3,000 kilowatt hours installed on board. This was analyzed in 3 different scenarios according to the market trends. So we have an average scenario, a minimum scenario, and a maximum scenario. And these analyses are based on the order book for new ships and on the experience on Damen and Fincantieri, in identifying, of course, the dimension of the energy storage system associated to the specific ship. This is the result of the analysis on in an average market scenario. We have the number of energy storage systems in 3 different time frame, up to 2025, 2030, 2035. We have the number of energy storage systems installed and the overall volume of megawatt hours installed on board. And we can see that in the first period, we have a high number of more than 3 megawatt hours energy storage system installed, but then this number stabilized more or less around 700 megawatt hours in the overall in the 5-year time frame. While we can see an increase in the installation of energy storage system from 1,000 to 3,000 kilowatt hours, sorry. And it looks like that mid-size application will see strong growth compared to the other 2 categories. And it also appears that the price and lower price and better performance of the batteries will make it more attractive to install medium-sized energy storage rather than energy storage with less than 1 megawatt hour installed. And here is a resume of the result presented before. Previously, we've seen the average estimation, average market scenario. And here is the overall of the is the sum of the data we've seen before in an average estimation. And then, of course, we carry carried out the same analysis for minimum estimation and maximum estimation. Of course, depending of the situation we will have in the next years, pandemic, wars, and so on. In the work package 3, we analyzed the trend price of the main chemistry of lithium batteries for LFP chemistry, LTO, NCA, and NMC LMO chemistries. And we can see that over the years we will expect a reduction of the price of energy storage systems, and this is highlighted also here in this figure, where the lithium-ion battery price outlook is compared between electric cars and waterborne transport. We can expect that also in the maritime sector, we can have a decrease like in the electric cars sector, and so to reach lower and lower price over the years. This, of course, regarding also the system, the battery system price, we can see what we said before, a trend of reduction of the euros per kilowatt hours of different type of chemistries. We have LFP in blue, and then NMC in red, LTO here in yellow. And these green lines, we have the typical range a ship owner can expect, or a system integrator can expect, of the cost of the installation of an electric energy storage system on board. Here again is a estimation of the. Here in these slides, we want to set the targets, analyzing the current state of art of energy storage installation for cruise ships and ferries, so for large ships. We have the current state of art, and then the target within 2030. We can see that here we have a number of expected total hours of operation, and here we want to have an increase in these numbers. Of course, we can see it here, where we can expect an overall higher number of equivalent cycles for energy storage systems. While it's important to highlight the fact that we want higher numbers of cycles. Here we have a battery cost target estimations. We compare the fuel price in euros per tons with the electricity price. Here we have 3 different scenarios: batteries with 3,000 cycles, batteries with 6,000 cycles, and batteries with 10,000 cycles. Of course, higher the number of cycles, better could be the cost savings when installing energy storage system. Here we can see when we have a number more or less near to 500 kilowatt hours or higher, we can have benefits, also economic, to install energy storage system on board. In the deliverable 3, we also want to highlight the bottlenecks and the challenges in the design of the future energy storage systems. And so we want to be, with this table, we want to be aware of all the aspects that have to be considered when installing energy storage system on board. And that, of course, energy storage system could be an issue for the ship itself. Then we're going into the last deliverable. So impact on battery production in EU and its circular economy. Here in this deliverable, we start to analyze the supply chain of raw materials for the production of energy storage systems. And we now we have a scenario where most of the raw materials are from Far East. And so in Europe, we are not able to produce this raw material. And so we have to buy it from other countries out of Europe. And also in the work package 4, we analyze the manufacturing process. So all the process from the raw materials to have the final cells constructed and then utilized in the energy storage system. This is fundamental because at the end of this presentation, we will see the importance of circular economy and so of the recycling of these raw materials in order to permit to EU to have this kind of material available for its necessity. In fact, here also there is foreseen a multitude of new lithium-ion factories all over Europe in the next years, from the less than 10 gigawatt hours capacity to more than 300 gigawatt hour capacity. And here we have the main companies and the location of the gigafactories and so on. So in the next years, we can have also on board ships battery manufactured in the EU. This is why it's important to analyze the raw materials and where they come from, because the aspect is to come from a linear to circular economy. And these are the main pillars of the circular economy. So it's not only recycling, but it's also smarter product use and manufacture, extend the lifespan of products and its parts, and is also an aspect considering the Seabat project. And then, of course, the final part of recyclability and recoverability of the energy storage system. Here, there is a study from the University of California analyzing the profit of the recycling of different type of cathode materials with different process. And as we can see here in the radar chart, we have different KPIs, and here in the table we have these different KPIs compared with the different chemistries. And so we can see that direct recycling method could be the most profitable compared to the others. And then we have also the profit compared by different type of chemistries. This is an important aspect, of course, to underline, because the economic aspect is one of the main aspects where you need to focus on. Finally, in the work package 4, we carried out a life cycle assessment analysis for 2 different type of ships. Small ferries, the LM ferries is an European project, and all the data are available in the European report of the project. And for Ro-Ro packs, so bigger ships with 5 megawatt hours installed on board. The results here, we have 3 scenarios. We have a conventional small ferry, so with conventional diesel propulsion. And then is compared to the same ferries with battery systems installed on board. The difference between the 2 scenarios here in green and in orange is the first in green is based on energy mix EU, and the second on renewable energy. It means that when the ship is moored at port, is with a cold ironing facilities, the batteries are recharged through the land power system, let me say. And the difference here, of course, if we have renewable energies feeding the port structure, we have a further reduction of all the KPIs in this case. So it's important both to have energy storage system installed on board, but in this case also to have cold ironing facilities supplied by renewable sources. This is the second case, the second life cycle assessment from the Ro-Ro packs. And as I mentioned before, we have 5 megawatt hours installed on board and a gross tonnage of 50,000. Here you can see a slightly different, highly different radar chart, but why? Because here in the first case, we have the scenario where the ship with the 5 megawatt hours batteries installed on board uses the batteries for the last mile coming in and coming out from the ports, and then uses the batteries when moored at port without cold ironing facilities. In the second case and the third case, we have a cold ironing facilities, so the batteries are used only to the last mile coming in and out from the ports, but when the ship is moored in port, is supplied by the land power system. In this case, we cannot appreciate a higher difference as in the previous example. But why? Because we have compared 3 different solutions, always with let me say battery scenarios, so not compared to the conventional diesel engine. In these graphs, we compare the 3 different solutions I mentioned before to the conventional one. And here, for all the KPIs analyzed, we can see a high reduction in terms of high percentage reduction exploiting one of the 3 methods used before. So when we have energy storage system installed on board, we have further reduction in all the KPIs, operational costs, and emissions and so on. So with this analysis, we can say that definitely energy storage system on board has a higher impact in all different kind of ships, from small ships to Ro-Ro packs. So thank you for your attention. And if you have any question on the results of the work package 1, I'm available for your question.
I forgot to say that people attending online, you can also type your questions in the chat because our colleagues are aware of that. Okay. I don't know if you have any specific question or comment.
Thank you for the presentation, Andrea. Of course, I've read the deliverables. I had to, and they were very interesting. But when we were writing these deliverables, the world was considerably different than today. In the meantime, we've had a pandemic, we've had a ship parked very terribly in the middle of an important canal, and we have a war. So in today's world, the energy sector and the battery sector has been shaken up. If you order something today, you pay double than what you paid last year if you can get it delivered. And if you can get it delivered, you pay double on shipping as well. So can you estimate what the effect of all these current events are on the maritime industry, and in particular on the business case for full electric ships or for hybrid ships?
Okay. Unfortunately, you are right. In the last months, the price of lithium carbonate rise a lot, 6 times higher price of lithium carbonate, and so this is is not an easy scenario where to analyze the energy storage system market. But for sure, what I hope is that the trend I shown you before will be the trends also when this moment will pass away, let me say, and so when the war finish and the pandemic situation will definitely end. Of course, these analyses are based on the scenario of the last year, because the Work Package 1 was carried out in the first 6 months of 2021. So without with a pandemic scenario, but without a war scenario. And so in this moment, also ship owners are a little bit scared of the changing in price of lithium batteries in this period. So I think that this analysis could be reviewed in the next 5 years, but I hope that for the 10 to 15 years, the situation will be the one I presented.
All right, thank you. And of course, we have the advantage in that sense that the fuel prices have also exploded. So that's
yeah. Thank you.
Any other questions? Comments? Okay. Thank you, Andrea. Okay, so our next presentation will be made jointly by 2 of our partners, Shashank Roy Chaudhry and Alessandro Macari. Shashank is a Master of Science graduate in Electrical Engineering with a focus on power electronics, and machines from the Department of DC Systems, Energy Conversion and Storage at Delft University of Technology. He has been working as a research engineer in the field of ships, electrics and automation at Damen Research and Development Department. And he has also been a technical consultant for battery-powered electric ships and mitigation of electromagnetic interferences. Alessandro is the Marine Research Development Director at RINA Services, Master of Science in Naval Architecture and Marine Engineering. He developed multidisciplinary competencies in ship design, shipbuilding, and strategic research and development activities applied to more than 60 passenger ships. Advisor of the Italian flag administration at the International Maritime Organization since 1994. He coordinates the Italian activities within the IMO correspondence group on low flashpoint fuels, and he actively contributes to the development of the regulatory framework on marine environment protection and on ship safety in a vast collaborative international network with a strong focus on innovation. So, Shashank and Alessandro, where's yours?
Thank you for the introduction. The second work package of Seabat focused on specifications and regulatory requirements of maritime batteries. In this presentation, I will talk about specifications, which is divided into the application metrics and KPI report. And then the final section is about regulatory requirements. The application matrix is where we focused on the basic requirements for maritime batteries and also looked into vessels where a hybrid battery, hybrid energy storage system like this would be beneficial. There are mainly 7 different types of applications for maritime batteries. There is obviously the full electric version. There is spinning reserve, load leveling, boost function, load smoothing, ramp support, and peak shaving. The classical approach for selecting batteries usually includes finding out what's the minimum energy required at the end of life, what is the maximum power required while charging and discharging, and the number of cycles. But then the C rate is also used to narrow down more on what kind of battery system needs to be on board. And a usual rule of thumb is to use 80% depth of discharge unless specified by the supplier that the battery system can go even further. But for a hybrid energy storage system like this, an alternative approach was used where the operational profile, here is the baseline profile or the baseline cycle here, and it can be divided into 2 different types of cycles, the primary cycle and the secondary cycle, where the primary cycle is a much more periodic version of charge and discharge cycles where the ship is usually in its regular mode of operation. But the secondary cycle, which is here a larger discharge, it is usually something which a ship does when it operates out of its regular operating conditions. As an example, here is the operating profile of a fishing vessel. The orange plot here is the regular operating cycle for the fishing vessel, but the gray line represents the secondary cycle. The secondary cycle in this case could be something like maybe when the ship goes to a repair shipyard, and usually leads to larger discharges but with less power. So the operational profiles of 34 different vessels were gathered, and they were divided into, they were classified into 4 types as shown in this table, and their primary and secondary cycles as well as C rates were divided into these types, where type A represents C rates of less than 1 C and less than 1 cycle per day. On the other hand, you have type D, where the C rates are more than 6 Cs and more than 7 cycles per day. Here is the application matrix of all the vessels whose operational profiles were analyzed. And if you look closely here, the Ro-Ro ferries, their operational profile, the primary and the secondary C rates and cycles, they fall into different categories. And for such a vessel, a hybrid energy storage system would be most likely very efficient, beneficial. But if you look at the first 4 vessels here, 4, 5, yeah, their primary and secondary cycles and sea rates, they are all in the same category, and a hybrid vessel, a hybrid energy storage system would not benefit such applications. If you look at the water vessels here also, it looks quite promising for the hybrid storage, as well as the harbor tug here. But yeah. Yeah. Since there are so many different operational cycles for different types of vessels, and also several different types of battery systems which are available in the market, 10 different properties of all these battery systems were taken into account from 30 battery systems manufactured by 15 different manufacturers. And a score-based system was used to analyze their performance, where higher the score, better the performance. Here's an example of system costs of all the 30 systems, and they're also representing the battery chemistries that are utilized here. Marine battery systems are usually in 3 different types. There is the high energy battery systems, the medium energy battery systems, and high power battery systems. But if we look closely on the cost per cycle of all these battery systems, we can also further include another classification here, and we call it the heavy duty batteries. And we define them as the batteries which cost less than 7 cents per euro per cycle. So in total, we come up with 6 different types of battery systems. Another very important aspect of maritime batteries is the system designs in which they are available. Because of limited amount of space available in the battery rooms, the module-based and the tray-based systems are most efficient in terms of space utilization because of their flexibility. But the racks and block systems, on the other hand, they are much more of fixed dimensions, and they lack the flexibility, but they come with integrated safety systems and cooling systems on board. So there is a compromise there. Upon analyzing the energy density and the power density of battery systems based on their system design, it's the energy density analysis, and it's the power density analysis. We find out that the module-based battery systems are most efficient in terms of weight, and tray-based systems are most efficient in terms of volume. So the next slides on regulatory requirements, and Alessandro will continue.
So, good morning again. It's really nice to be here in presence, so I have a podium again and the possibility to see real faces. So I think that the previous speakers gave you an overview of the complexity and the large variety of solutions that we have available at the moment. There is the problem of managing the complexities. And probably the regulatory framework is adding additional complexities on that. You see on the screen that we have a number of current regulations, rules, guidelines, codes, and standards that are applicable or would be applicable to marine battery installations. All these definitions are not equivalent. It is sort of a jargon because we intend regulation, the international regulations, those written by the IMO, for instance. Rules are typically written by classification societies and are normally mandatory. Then we have a variety of guidelines, not necessarily mandatory, but that can become mandatory if a flag states decide accordingly. And we have codes that can also be mandatory or not mandatory, depending if they are related to the international convention or something different. And then the standards that are not necessarily relevant to marine application, but can be derived from other industrial fields or transport mode. So sort of a universe of regulations or rules or whatever, and in this universe, different worlds that do not necessarily are connected one to the other. In this specific work package, we have gone through what is available in terms of class rules and also international rules, and have selected a number of classification societies that combined together, you see them in alphabetic order, provide a very good coverage of the existing rules that we have available. Sorry, the other one. So, where do we start from? The origin of the marine regulations are pretty conservative, starting from the lead acid batteries that have been used and still are used for many, many applications, including the emergency source of power on board. We are facing now the rapid transition to other technologies. And in general, from the new technologies, there is still a relatively new market or low experience in this application, and we are learning pretty quickly, but not necessarily the regulatory framework is following the same pace of the innovation and the technologies. So somehow the regulation have to catch up with the real world and the industry. For the lithium batteries, today, the regulatory framework is still fragmented and based on conservative principles, so starting from the old technology and trying to adapt rather than revising completely the rules and regulations. And there are some references or cross-references to the IEC battery standards, but mainly for testing the batteries and the battery cells. In this framework, you do not see specifically the integration on board. That is one of the key issues. So normally when the regulators do not have readily available prescriptive rules, have the magic solution that is a risk assessment. Risk assessment is obviously something quite important, but not necessarily simple to carry out. And the risk assessment is ship specific. So you have to do that for each and every ship, and you cannot generalize the results and the solution. More than that, today we have no specific international standards that are readily applicable for marine battery systems. So complexities. Now, in the project, what we try to do, or what are the activities related to the regulatory compliance? Of course, the primary scope of this assessment is the safe design, the construction, the testing, the certification, the installation, and the maintenance of the battery systems until the final scrapping of the ship. So, as always in the research projects, we start at the very beginning with the identification of the regulatory gaps and the possible barriers. So we paint the situation as is. We work throughout the development of the project, in order to support the designers with the rules that we have for the development of the technology, the solution, the alternatives that we have already seen. And then at the end, wrapping up the lesson learned in the project, we have to understand if we can somehow remove the barriers or add specific knowledge in the regulations to pave the way for the innovative application on future ships. In terms of regulatory requirements in general, it is possible to have a variety of breakdown of the possible components of the battery systems. This is a typical example, could not be the standard one, for sure. In covering the regulatory requirements, we start from basic design, construction, location, installation on board, all the equipment, and managing the power, electric protection, fire safety, and to the end, to the certification process and operation and maintenance. Breakdowns are always tricky, can be dangerous, because you try to consider the items one by one, and maybe you lose the possibility of having the complete picture. Because whenever you discuss, I don't know, the fire and explosion safety, this is related maybe to electrical protection, or related to ventilation, or battery charging. And so it's very difficult to follow a strict breakdown. It is, of course, easier to go through these aspects one by one, but having always in mind that we are discussing a single integrated system in a ship. And that is a clear problem, or something that we have clear in mind when addressing this kind of solutions. I mentioned the integration on board that, at least for a classification society, is the highest priority. Because in general, we are not, well, focusing on the single performance of a single battery or a single cell. We are interested in the safety of the ship and the reliability of the ship at the end. So the problem is always the electrical network and the integration on ship. You have seen a variety of possible ships in terms of power installed, operational profile, size, dimension, area of operation around the world. So what is of paramount importance is to have always power availability to the ship essential systems. It is clear that we have to prevent a blackout on board. The ship should never stay dead in the middle of the sea. And for this reason, we defined broadly as essential systems those related to propulsion, power generation, directional control, steering, and communication, life-saving appliances, all the systems that must remain operational related to the power source you have on board. So safety, ship essential systems, and this is also related to, or directly linked to, the energy management system on board, and the monitoring, the control, and the possibility to have the situation always under control. So there are some safeguard principles that will be applied throughout the project, starting with the individual control systems for each battery. So starting from the individual components, individual separation of the cells, the protection of the battery space, and the protection of the space where the batteries are located from external hazards like fire on board that could propagate into the battery rooms. It is also of paramount importance to have remote control, alarm, and safety systems to understand immediately what is going wrong or what can possibly go wrong in the operation of the ship. And also the thermal insulation and the operational requirements and conditions are always difficult. You see from this broad list of items that it is rather difficult to have a single solution or a single prescriptive requirement that could cover all the possible application in all possible ships, because most of these technologies need adjustment, need something to be tailor-made for an individual ship application, even if it is limited power or energy or a higher power demand. But these are some sort of cornerstones in order to guarantee the basic safety of the ship and the availability of power to the ship essential systems throughout the life cycle. And of course, this must be ensured also by proper maintenance of the ship and the components throughout the life cycle. Now, we are addressing in this project, also in general, in other industrial projects that are running now, novel design features or principles on board. So all these aspects are not covered by existing rules and regulations. So we have to go through case by case using a risk assessment. Risk assessment is not black magic, but requires a lot of activities, a lot of experts, and a lot of time and resources to go through a comprehensive risk assessment. But it is mandatory whenever we have no explicit rules to cover the situations. And another possibility that is also rather well described and addressed by classification society is the so-called technology qualification process. Technology qualification process is a process, a methodology that is required or should be applied whenever we have non-conventional solutions or technologies. So being a methodology, this is sort of a guideline for the approval process of the novel technologies, providing the criteria for the equivalence of the new design features, how to go through experiments, calculation, testing, and other supporting information, and gives also a procedure for the failure mode and effect analysis, the FMEA, that is aiming at preventing that a single failure would stop completely the system. And then the requirements and compliance criteria for the operational safety, including the instructions for the personnel on board, what they should do, what they should not do, and possible operational limitations related to the type of ship and area of operation, and listing all the possible design uncertainties and safety margins, because we are dealing with novel designs. We have no feedback from the past. Trying to understand with the risk analysis what could be the internal failures, but also the qualification of the components, the materials, the battery cells in this specific case, and also in terms of construction, quality control, quality assessment, construction criteria, and test on board, and throughout the life cycle of the ship, health monitoring and possible damage detection and the quantification and repair, what to do if something goes wrong. So again, methodologies, criteria, but not strict prescriptive requirements. What if we identify gaps? We know that today the regulatory compliance is not perfect, far from being perfect, and in working in the project, we will keep discovering additional possible regulatory gaps. So after the initial review of the rules and regulations in the project, dealing with the static, but also the dynamic design, the material certification, testing, and everything, there will be aspects that will need additional attention. So regulatory gaps means also there is some learned in the project. We will be specifically active towards the end, but still today accumulating what are the gaps. And we know already that in terms of rules, we are not covering enough all the dynamic phenomena that are happening on board. We are not properly addressing the failure modes of the different batteries, and also the behavior of the batteries in extreme temperature range where the ships can operate, the aging of the batteries in these conditions, and in general, what I call the marinization of the equipment, that is also including not only the marine environment, corrosion, salinity, humidity, but also the stresses and the acceleration that you have on board due to the ship motion, rolling, heaving, pitching, and so on. The possible consequences on the battery system of fire or flooding on board. Even a minor fire or a minor flooding can have a strong impact on the battery installation. And then, of course, the fire management, so detection and suppression system for the, especially with lithium batteries. And open a parenthesis just to confirm that the European Commission is actively leading a group on the safety of ships, and specifically Ro-Ro ships, RoPax ships, and car carriers that have lithium batteries or vehicles with lithium batteries as cargo. And so the thermal runaway, the possible fire on board is a huge problem. And there is a strong effort and coordinated by the European Commission, DG Move, in order to address and try and solve this problem that could lead up to the loss, the total loss of the ship. So you understand that batteries, and including vehicles that are carried by ships, bring additional risk to the overall maritime environment. And so we are involved as also as RENA in these working groups in cooperation with DG Move, EMSA, and of course the European member states in order to bridge some of the gaps of these still open list of issues. We can learn also from other industry application, other means of transport. We have gone through, with the assistance of other partners in the project, through a number of standards, international, ISO, IEC, and other specific for other means of transport. I will not insist very much on that. There will be other presentation, I think, on this specific topic. And just concluding, not only saying that we have gone through all the activities of the work package, completed everything on time and with the proper requirement. So the work package 2 is just the beginning. We will continue monitoring the activities throughout the project and wrap up the conclusions at the end. Let me just finish this intervention with a comment in general on class societies. Class societies in the past just received the drawings from the designer, from the shipyards, and put in some maybe nasty red marks at the end with approved, not approved. That was the past. The situation is completely different. Class societies are partners from the very beginning. We have not to wait to receive a final drawing, a final design, to have comments on that, but we are involved from the day one of the new designs, together with the designer, together with ship owners, together with flag administration, in order to prevent problems and make sure that the final design will be fully compliant with the rules. And that will saving time, money, and give for sure a better perspective on the final results. I will stop here, maybe been too long, and of course available for any possible question or comment. Thank you.
Is there any question or comment? Maybe people attending online, I don't know. No? Okay, perfect. Thank you,
Thank you.
Alessandro. Okay, so let's have a break, 30 minutes break. We are on schedule, so coffee is being served in the hall, and we will meet again here at 11 o'clock. Okay, thank you.
magic. I'd clean up the whole mess. If I had magic, I'd clean up that awful mess. But I'm just a working man, and I'm hoping for the best. If I had money,
Okay, welcome again. I'm going to introduce you our next speaker, Sudarshan. Sudarshan is a diploma engineer that studied automotive technology and received his master's degree at the Eindhoven University of Technology. In 2017, he became associate research engineer at Flanders Makes in Belgium in the Decision and Control Systems Research Group. His expertise includes different lithium-ion battery systems, hybrid and electric vehicles, energy management strategies, context adaptive control, lead-acid battery systems, state of charge and state of health estimation algorithms, and algorithms to decrease the battery aging. So, Sudarshan, first yours.
Hope you guys can hear me. Yeah, thank you for the kind introduction. So today I will be presenting on the topic of design of hybrid energy storage systems. This is the work we did in part of the work package 3.1 deliverable. So yeah. So I will be going through the main contents which is given here, the problem statement, the topologies, different hybrid storage systems, the use case which we took, and how we optimized the battery system, and some results and conclusion. Yeah. So the problem statement. So why hybrid energy storage systems? As my colleagues have already explained, it satisfies the requirements better because we can customize the energy of the high energy and high power batteries to suit the requirements of the application. Therefore, we can also reduce the oversizing of these energy storage systems. So that's already clear from my colleagues. But the problem is, how do we have an optimal system design of these hybrid battery systems? How do we do this? And what we need is actually, we need the lowest possible system size of both high power and high energy batteries. But it needs to also follow the load cycle and the requirements and so on. But this lowest possible size, it also has another thing, that you need an intelligent smart algorithm which is optimal, which tries to distribute the power between the high power and high energy batteries in real time. So we need this optimal power split. How do we decide that? And how we go across this? Because if it's not optimal, the power split, then your system design is also not optimal. So we try to tackle this here. And the next thing that's the advantage of using the approach we do is that we can compare different topologies and see, okay, which topology is good, because there are lots of topologies in hybrid batteries. And how we solve this in 2 words or 2 lines is that we combine the optimal sizing with the control, and we perform a code design optimization. That's how we call it. And then we try to combine all the system parameters together, and that's how we do it. I will explain this further in the next slides. But first, let me just give you a brief overview of the different hybrid energy storage topologies which are there. So it's broadly divided into 3 categories: the passive, the discrete, and the active. The passive system, as you can see, it's both the high power and high energy batteries are directly connected to the motor, which is the load, through the inverter, and there is no DC-DC converters. So the problem with these is that the voltage range of these batteries has to match the load perfectly, and then the inverter can only do a little bit of different voltage input, so it can tackle that, but not much. So the range of operating voltage of these batteries is limited. So this is not really used in many of the systems. So it's, but this is one of the options, but it's less common. And the other, the discrete batteries, I will go to next slide. I will explain in the next slide. But the active one is the popular one, which is being used in the battery industries, both in maritime and automotive and so on. So here it's again divided into 2 broad categories, such as semi-active and active hybrid storage topologies. So now I will describe one of the systems of the semi-active. As you can see over here, you have just a single DC-DC converter, which tries to balance the load from the high power and high energy. So, and is connected to the load. So this is the parallel design. So both the high power and high energy is connected to the DC-DC. So that it gives some operating advantage that, okay, the voltage, it just tries to match the requirement of the load voltage to the battery voltage through this DC-DC. So and there's, it can also do some power split, how much it can go for the high power and high energy. So that is one of the good things. The other more common ones and more complicated systems is having the 2 DC-DC converter with full control over power distribution and flexible ESS operating voltage range completely. And here we have the ultra cap and the battery, but you can also have a high power and high energy. It can be anything. So that's broadly. And next I will describe the discrete hybrid systems. They are not so common, but they are being evolved, and there are lots of prototypes already on the market, and some people also use it. What does the discrete battery system do? Okay, first let me explain what is a fixed battery system. We have fixed interconnection between these cells. So these are all fixed. So and then you need a DC-DC converter, and then you have the power electronics, and it's connected to the DC bus. And the DC-DC converter regulates the load. Of course, so you need it for a good system. And then what does the discrete battery system do? First of all, the discrete battery system has more cells than what is required for application, but it also has a lot of switches. And then it tries to get rid of this DC-DC converter, which is also one of the cost consuming component in a battery system. So how does this do? I will explain in the next slide. But the main idea is to have the switches in each of these cells in the battery, which can connect and disconnect accordingly. The switching elements, they try to connect and disconnect to balance the output voltage of the load. So that the voltage of the load is same. So if you need 1500 voltage at the load, it tries to mention, okay, I need so many cells to engage, and so that it's approximately that. I will get back to on that in the next slide. So how does it do it? So for example, it depends on the state of charge. So it's an algorithm in itself. So if you have a full 100% SOC, and so approximately let's say that if you want 1500 voltage, so 357 cells are engaged and the others are not engaged. And then as a SOC, you or discharge your battery, then you need to engage more cells to keep the voltage at 1500. So it will not be perfectly 1500, but 1 or 2 volts here and there, which can be taken care of the inverter. So that's how the discrete systems work. But of course, it need not be the same cells which are engaged. So the cells which are engaged and disengaged can be different. So, but the next advantage of this having the switches is that in a fixed battery system, if one of the cells gets empty faster than the other cells, you need to stop discharging. But in a discrete battery system, even if one of the cells gets stopped, you can just switch them off and then start engaging the other cells and discharge through that. So that's the advantage. So you have extended energy delivery, and you can use the complete energy of the whole system. Yeah, and also the balancing. You don't need a separate balancing circuit because you have the cells, the switches in itself, which does the balancing. And then it's also having a good fault tolerant safety, because if you know one cell is faulty, just disconnect these cells, and we don't need to disconnect the whole module, and we can monitor the cell very well. So that's a good thing. Based on the different topologies, we selected 2 topologies for comparison. As we cannot, we cannot compare everything. It's a little big, but this is what we thought will be good to compare: the discrete and the baseline. Baseline monotype is a typical system, like you have the battery, DC-DC converter, and a motor. But for a discrete hybrid battery system, we made some use case and calculations and came to this kind of a system where the high power battery is the normal battery without the switches. It's a typical one. And the high energy battery is the discrete battery. And then it matches the load of the motor, and the DC-DC converter takes care of the high power battery. So this is what we selected, and now we will be making a simulation for the use case specific to a use case, and trying to see, okay, how do we design it and do the optimization. Yeah, so for this we selected, we did the use case on multiple applications, but the application which I'll be presenting today is the Ro-Ro ferry one. So this is what it looks like. We got this from Daman and other companies. So this is a Ro-Ro ferry one application. It has 2 kind of load profiles. The primary profile, which is typical in the summers, which is also mostly running in most of the time in the year. It's 335 days. And the other secondary profile is just running in the winter, the 30 days, which is the most worst case scenario. And it needs a lot of energy, you can see. And also the power demands are like around 2000 kilowatt compared to 800 kilowatt in the primary. So that's how the cycles are. So this is what and we think the hybrid will be a good scenario, hybrid batteries here, because you need a high power, and there's also a lot of cycling and energy. So it's you need to balance these. So next, for the system design, we used a simple model for the batteries. The state of charge model, they are same for the baseline and LTO and the NMC. So NMC is the high energy battery we selected, and the LTO is the high power batteries. And the values for the capacities will change, because if it's a discrete, it will be different. And we try to model the state of charge as a simple one, and we assume 100% efficiency. But with our approach, we can also have more detailed models, but we chose this as to be easier to compare with other partners, so on. And of course, we limit the SOC to 10 to 90%. That's what most people do to have a safe operation and have this emergency use of the 10% at 90. And then the battery lifetime model is, the battery lifetime model, so we need to model it for, the requirement is that we model it for 10 years. And then we consider both the cycle aging and the calendar aging. This is like how we do it because we have 2 cycles. We need to calculate the ampere hour throughput for the primary cycles for 1 cycle, and then multiply with the number of cycles in 10 years. And the same for the secondary cycles. And then together we compare with the cycle life of the batteries to arrive at the cycle aging. So this, again, here we had to select a simpler methodology because having more complicated models makes the optimization complex. And not only that, and more information is required specific to the cell and the manufacturer and so on. So that makes things difficult. And such information like a cycle life will be available with most manufacturers. So it's a good way to start. And for the calendar aging, we assumed 1% of degradation of state of health. That is the aging. And that is depending upon the year of number of seconds or months or years of standby. But the 1% is for a year. And then we assume that the battery goes to end of life at 80%, which is also typical standard things that we use in automotive and maritime. And then what we want to minimize. So we want to model everything together to minimize the least cost effective. So we take all the costs, mostly what we can model, but there are other cooling costs and other things which we try to ignore it because it makes things complicated. You cannot take everything into the thing, but maybe in the future, if you can model the cost, it could be good. But we have the cells cost and the DC-DC cost for the baseline topology. And the cells cost is like the number of cells and cost per cell. And we try to model these costs as a function of this unknown parameter, which is the capacity of the battery, because we want to find what should be the capacity of the battery. And the cost of the DC-DC is like, we also made it simple here, the cost per kilowatt, and the DC-DC has to be sized to the load cycle. So it should be able to satisfy the max of the load cycle, which you get. So that's we have the load cycle, and we assume that the DC-DC is sized to the max of the load cycle. For the discrete battery, we have more components compared to a baseline. So here we have the high power cells and the high energy cells, and then the high power DC-DC because it's a normal battery. And then here we don't have the cost for the DC-DC for the high energy because there's no DC-DC in high energy, but you have an extra cost as switches. So how do we have the same thing as before for the baseline, number of cells into cost per cells, and then the capacity of the high power and high energy battery is the parameter, and we need to find out. And then for the switches, and for the switches we have to assume 2 switches per cell for the design for the safety, because switches could determine whether they're safe. If one of the switches fails, then it's not good. So we always want to have 2 switches per cell and also a control circuit. So, but this we assume that, okay, since the integrated circuits and things are getting cheaper and cheaper, it should be cheaper than the DC-DC. Yeah, so how do we optimize? So first we define optimization parameters. So that will be the capacity of the battery, just the capacity of the battery for the baseline. For the discrete, it will be the capacity of the batteries and also the power split. So how do we optimize? Because we want optimal power split. So it's not a simple optimization. We have the power split at for the primary cycle and also for the secondary cycle. So we try to optimize everything so that we have the best design, this optimal system design, but still not so optimal because we have to take into the thermal cooling and so many regulations and things. So, but at least to an extent, it's a lot more optimal if you consider all of these as a system. And then what we try to do is we model the system of the batteries and the DC-DC as a function of these optimization parameters, which needs to be found out. We do not know these. So for application of Ro-Ro ferry, what should be the capacity of the high power battery? What should be high energy? How do you split the power between these two? And so on. So we try to model these, as I already stated in the previous slides, how we model these in terms of the optimization parameters. Yeah, the baseline is the NMC we chose, and the high power battery is the LTO, and the high energy is also the NMC. That's what we chose. And we try to make a lot of constraints. These are the main constraints, but there are lots more. So the SOC range is between 10 to 90% and the 80% capacity, the charge and discharging power of each battery, and then the required power of the load cycle, everything has to be met. And there's an extra requirement for the discrete high energy battery, so that it needs to have minimum number of cells to match the load voltage. So that it's we limit the number of amount of capacity for the high energy. And then what we minimize is the topology cost, and which was already described in the previous slides for the two topologies. And this is not a simple optimization. The thing is, because we use, it's difficult because we have a lot of parameters for the discrete battery. We have two parameters here, and this is not a third parameter because we have power split at each sample time. So there are, like, if you have 1,000-second power duty cycle, we have 1,000 parameters. Or if the sample time is like changing 30 seconds, then it's 100 parameters and so on. So for this, we use a special technique called a direct multiple shooting optimization technique, coupled with a toolbox which we already developed in Flanders Make, which is quite generic and usable in multiple applications. We try to use these to handle the scale of the problem. And this is how the optimization looks. Here we performed the optimization only for the power split, assuming the capacity is known. So we just simulated it for one capacity to get an idea of the optimization and its power. So this is how the set of charge varies, and this is what it said. Okay, this is the optimal power split. Like, okay, this much power has to go into the NMC, which is high energy, and the LTO, and that's how you satisfy. The negative power is just the discharging. So, and then you can also need to the constraints for tracking the reference power profile. It's very good because 2 × 10⁻⁻10. So it's very good, and then this is how it looks, and then you can see that it varies with different time instant, and this will be done over different capacities. That is also combined later. So we have optimal power split with different capacities. If you go for rule-based things, generally you need to optimize one parameter, but here you have lots of parameters and it's more flexible. And typically is very useful when you have more higher complex models of the batteries. And here we combine both the power split and the optimization, the sizing, both. So here for the secondary profile for the Ro-Ro ferry, you can see that the LTO batteries typically, so this is like this is a fresh battery, how the state of charge movement looks like for the optimal system design. And then after 10 years, you can see that when you perform this load profile, it goes to the 10% state of charge, meaning it is like end of life. If you cannot even perform one cycle extra, then it would have aged more, and then it will need to go below 10%. But it's not the case for high energy NMC because you need a higher power requirement. So we have to a little bit oversize that. But this is what like an optimal system design and the graphs look like for different periods of usage of the battery. And next slides, I have the results. So the results first on the cost. So we compare the baseline battery topology cost and the discrete hybrid after the optimization. You can see that there is around 13% reduction in the discrete hybrid battery, which is a good thing. And the cells cost is a little bit down, and the NMC cells cost, it's a lot less for the discrete hybrid because you have also the LTO. And the high power LTO cells, the DC-DC plus switches cost, you can see this, that for the baseline it's more costlier, and for the DC-DC converter, when you replace it with a switch, high power DC-DC plus a switch cost, It's cheaper for the discrete hybrid battery topology. So that's a good thing that the discrete hybrid topology makes things cheaper. That's good. And here the energy capacity. So you can see that how the baseline energy, total energy of the baseline is like 3,900 kilowatt hour, which is quite high compared to the discrete hybrid, which needs only 2,200. So that's where we have this hybrid batteries coming into place, because you can better suit the requirements. Because the baseline battery needs such a high energy, because you need a high power for the load cycle. So that's why you have need to oversizes. And the discrete battery topology is much cheaper. And it says that I don't need so much energy. I just, it's enough for if it is 2,250 kilowatt hour approximately. Yeah. And one more thing is like LTO battery is quite costly. Yeah, you can see from the fact that that the NMC capacity is more than the LTO, and then but the cost for the LTOs are much higher than the NMC here. So yeah, so in the future we will have more cheaper. Hopefully we have more LTOs which are cheaper after because if it still needs to get mature and mass produced more and more, so that it will get cheaper, and then we can see much better use. There's the results, which is wonderful to have these, yeah, and say that okay, now we can clearly say that the discrete hybrid battery system costs cheaper with the high power and high energy compared to the baseline with the high energy NMC. And then it comes to the conclusion. So we have compared the different battery topologies. We have a good approach to find the cost-effective topology, and this can be reused with different cell chemistries, different topologies. It's pretty easy to optimize and so on. Yeah, we have the total cost of the system with all the constraints and so on. Yeah, and we come to the conclusion that discrete hybrid battery topology is cost-effective compared to the baseline for this application case. It could be different for other cases. So that comes to the conclusion or end of my presentation. Any questions? I guess not. Okay.
Are there any questions?
There is a question online.
Mm-hmm.
Simre is asking what C rate was used for the different systems in this case.
What C rate?
Yeah.
C rate.
So we actually compared. So the NMC could, I think we use the Samsung NMC specifications, and for the LTO we had the Toshiba. So for the LTO we had a C rate of 4C max, and for the NMC we had I think 1C or 2C. Yeah. But we took the battery capacities from the manufacturer's data sheet. So these are what is actually being available in there. So.
There is another question. James is asking, or is saying that very interesting your presentation. Which KPI do you find important for this research?
Which KPIs? Oh, it's a cost, I would say, but it's just not the cost, because if it's not safe or other things, it's not useful. And here another thing which we miss here is also that the weight, because if you are weight is an important category, I think, in ships, because if it's heavy, then it needs to pull more power. So it's the cost, weight, and safety regulations, so on. That's what I think is most KPIs. I think maybe my colleagues will present more detailed different KPIs. I think Daman presented a big list of KPIs, which they think the cost and requirements and so on. But Yeah, but here I can assume only the cost, but I think both cost and weight and everything is important.
I'm not asking a question, but I would like to reply to the question online also from my side. So what is interesting here is that the tool is capable of trading off various KPIs for a specific design that you want to achieve. So indeed, in the previous presentation, we listed a bunch of KPIs that are really interesting. Some are hard requirements. It needs to be safe, but you can optimize for weight, you can optimize for volume, you can optimize for cost. These are all trade-offs. What is interesting is that in your criterion for your optimization, you can try and assemble a mathematical formula to trade off all these with a certain importance for your application. So it may be that for Roro packs, it's more interesting to have a lower weight or to have a lower volume, and then you give more weight to this element in the total criteria for which you optimize. So in the particular case that is being presented here, I think we targeted more towards the cost, and we took the various costs elements into account and taking into account life cycle as a requirement. And so indeed, here are the mathematics, but the tool itself is flexible for you to assemble a certain target for the optimization in which you can trade off any KPI for which you have the information for it to be calculated. And therefore, I think the list of Damen is a very interesting one, for example.
Yeah, to add to that, how we can add the weight is like you have the cost of the cells, and it's a function of the capacity of the batteries, and you will have also the capacity of weight. If you know the specific energy, then you know the weight of the batteries. If you know the capacity, so you can just add a couple of terms here, and if you can also add some weighted functions to add more things like weight, but of course safety regulations and other things you cannot add. But yeah, you can have a good trade-off and play with this tool and have more things.
Yeah, the difficulty typically is to find the correct translations to put them all in the same equation. So you would say, if you would do it on a cost basis and you would optimize the cost, you could say that for every kilogram it would cost you a certain amount of, or it would add a certain amount of euros, and then your total optimum is still cost, but weight is taken into account into the cost formulation. So that's an example on how to take this into account.
Okay, please, Ramon.
Hello, interesting concept regarding the discrete battery. One small question regarding the how can if you have thought how can you manufacture this issue, no, regarding those cells that will open and close, no, to that, and regarding the reliability that you think that to having so much switches that could be even 1,000, no, could perform in this type of systems.
How to manufacture is something to Imakar, but yeah. But indeed, it is difficult and to have a reliable, functionally safe all the time. And we need to monitor this, each cell, whether the switches perform correct. And then we have, if you can monitor and see, okay, if the switches fail, then you can easily at least make sure that module is being separated, and then it's being reported to the technician on board in the ship, that they can easily replace all the switches, because the switches should be cheaper, or we have now backup systems. But indeed, that is one of the things we really need to make sure that the switches. But we need to have a separate control circuit and so on to control these switches. And how do we? Yeah, so we assumed something like we made a preliminary design for this control circuit that could be attached on top of the cells. It came around €5, so it's not too costly, but the controlling, it will mostly we localize the control circuit to the cell or to the module level to have that particular voltage. But the reliability is a big thing, so that's why it's not broadly adopted in a lot of industries, but places where you need safety, medicals, or other kind of things, you can use this, and if you can have your the switches, you know whether the switches fail or not. If you can identify that, then it's useful.
if I may complement the answer again, thank you for the question, by the way. We had 3 topologies that we had investigated in the Seabat project, and this was one of them. And indeed, reliability and manufacturability was one of the major challenges here. So from a theoretical point of view, it was a very interesting topology to research. But we did find an industrial company it's a scale-up who is investing in this discrete topology. It's called Nerve Systems, based in Australia. And we reviewed a lot of their information with regards to feasibility and so on whether this would actually be functional. And we invested a bit on indeed getting this controller done, trading of the different ways of getting the switches aligned, how it could be manufacturable and so on. But in the end, this topology is not the one that we will continue in Seabat, because another topology, which has, we call it module level converter, so a converter per battery module, was more promising with regards to, amongst others, manufacturability and so on. So for now, it continues to be an interesting topic to research, but we also we wanted to show this topology here and demonstrate the feasibility of the optimization tool. But it's a very relevant question and remark.
Yeah.
Thank you. Just a simple question. Which is the source of the cost cell? I mean, you know that the price of the cells depends a lot of the purchasing volumes. Which is the source that you use for these numbers?
The cells, we got this quotations from Samsung and Toshiba. So at that time, it was Toshiba gave it in Japanese yen, so we converted into euros, depending on the exchange rate at that time, and we assumed a mass production for I don't know the exact number for the number of batteries cells. We got this, and same thing for Samsung. So I think this also was done by Imacar. It was a collaborative project, so I think they were handling the information, but we assumed it's mass production, and for particular numbers, we got the estimates from the Daman, the number of ships they will produce and so on. So we did a calculation like that.
Thank you for your talk. Just one question to this RoRo concept with this 37 cycles per day.
Yeah.
If you're going back, this means you have a charge-discharge current of 3C at the end. And do you mean with complete cycles between 90 and 10% state of charge in this case?
Yeah. So we assume that one complete. No, the battery is sized in the perspective that they go to charging after one cycle. So you have maybe it's easier to see in the secondary profile. So after one cycle, that is the one after which they go to the charging, and this is they charge here, and then they again discharge and they charge. So the battery has to be at one charge between 10 to 90%. They start at 90. At the start at 0, and then they have to end at 10%. Minimum.
To the primary profile.
It's the same. You have that both the charge and discharge, but there are more cycles, so it's difficult to see here.
So you discharge the battery in 20 minutes and charge it again in 20 minutes.
No, these are like you can see the numbers are 20,000 hours. So these are 10,000 hours. So the discharging will take days. I think it will take lots of days. I don't know exactly if we have to count. It will be for 5 days or 10 days. We will have a load profile, just the discharging. So
I was just wondering about the 37 cycles per day.
It's 37 cycles per day. Yeah, okay, and that's true. Sorry, my bad.
Question was, because this includes that you have 20 minutes discharge and 20 minutes charge.
Oh, sorry, it was 37 cycles per year. I think there was a typo. Yeah, it's 37 cycles. It's the complete cycle. It's for a year.
Yes.
There are 7 the understanding I get is there are 37 cycles per day, but those cycles are not full cycles. If you look at the energy content, is much less than the energy content of the battery. So these are shallow cycles. So what they call secondary profile, those are probably deep cycles. Yes, that's the that's where it comes from.
Yeah, maybe to add to that, I can show in the after the optimal system design the results, because this is just one cycle does not mean one complete battery cycle. But in your reference here, after we performed the system design, so it starts from 90 and it ends at 60% state of charge. So you can see that it's for the battery, it will be like less than half a cycle, but for the application, it's one cycle.
Okay, that makes sense. Thank you.
Yeah.
Also, I was wondering what's the lifetime of the battery will be, because with 3C charging, discharging, it will rapidly degrade.
Yes, exactly. True. Any more?
Are there more questions?
Okay.
Yeah. Thanks for all the
Thank you,
questions.
Susan.
Yeah.
Okay, so let's move on to the next presentation. It's an honor to introduce you the following speaker, because he's my colleague. Eric Garayalde received the Bachelor of Science degree in Industrial Electronics and Automation from the University of the Basque Country in 2014. And thereafter, he received the Master of Science degree in Energy and Power Electronics and the PhD degree in Electrical Engineering from Mondragon Unibertsitatea in 2016 and 2020, respectively. He is currently a researcher and lecturer in the Department of Electronics and Computer Science in the Faculty of Engineering at Mondragon University, and his current research interests include renewable energies, energy storage systems, and power converters. For the latter, the modeling and control of the bidirectional power converters for battery applications is part of the work that he is currently working on. So, Eric, over to you.
Hello, everybody. Thank you very much, Arvigne, for the introduction. I think that the microphone is not working. Yeah. Well. Yeah. Okay, no problem. I can continue here. Okay. Okay, I'm going to talk to you about the modular partial power concept for this particular application. And first of all, I'm going to start with a brief introduction, and it will be very brief because I think that everything here has been already mentioned before. After that, I'm going to talk to you about the hybrid energy storage system design, sizing. After the partial power converter, the simulation with the simulation and experimental results. And finally, the conclusions of our work here. Well, the energy efficiency is one of the main roadmaps for Europe in the upcoming years. The reduction of fossil fuel dependency, the CO2 reduction, improving the efficiency. Here, the energy storage systems have a very big importance. And in the maritime industry that we are talking about, as it has been already mentioned, the International Maritime Organization wants to reduce the total amount of greenhouse emissions for 2015. And what are the main advantages of installing energy storage systems in the ships? Well, we have the peak saving, energy harvesting, backup power, and others. But the big question here is, what are the main challenges for electrifying a ship? Well, first of all, the selection of the proper battery technology. and the sizing of that battery pack. Well, we have different kinds of energy storage systems, these different technologies, some of them with high power density but low energy density, others with high energy density and low power density. But can we combine both? And of course, yes, but how? We want to obtain one energy storage system capable of combining both capabilities. Of course, there are some lithium-ion technologies that can fulfill both, but in terms of price and other aspects, maybe those are not the best option. And about the hybrid energy storage systems, first of all, why do we need a hybrid system? Well, the first point is because of our application profile. We have average consumption and power transients. So if we want a perfect sizing without oversizing in terms of high energy or high power, we have to combine two batteries and we will obtain the optimal solution. And about the sizing, there are three main points: the power sharing method, the application power profile, and of course, the cost of the batteries. And the first step is to select the power sharing method. There are different power sharing methods. For example, rule-based control, typically used for photovoltaic systems or predictable systems. Filter-based power sharing, typically used for electric vehicle because the power profile is more or less unpredictable. And virtual impedances or droop control, typically used for microgrid applications. In our case, we are going to focus our efforts here and specifically on the first one, the power threshold, because it's simple and it's enough for us. So it's as simple as putting a power threshold to separate the high power from the low power, and we can separate the power profile into the high power battery and high energy battery. And in our case, the high energy battery will be the NMC. The size of this battery is going to be the main consumption of the application, and the maximum power is limited to the previously mentioned power threshold. The high power battery is going to be the LTO battery. It should provide the rest of the power of the application, and it is able to work with high dynamics. And both have to work in a complementary way. Taking the data into account to fulfill our application power profile, we have to fulfill a service life of 10 years. The end of life is considered as the 80% of the initial capacity. We have some power and energy requirements. The DC boost voltage in our case was fixed to 1000 volts, and the state of charge range, at least in the beginning of life, was between the 90 and the 10%. And with all this data, we have to run our algorithm to size this application, this battery pack. First of all, we have to introduce the battery data and the power profile. After that, we apply the power sharing method and we test it for 10 different power sharing levels. We will see that later. After that, we consider the energy required to fulfill the application, and we compute the aging of the battery, taking into account the depth of discharge, depending on the power profile of the application, and the energy requirement of both batteries. And we after take the most restrictive option. And finally, we check if in the end of the life of the battery, we comply with the energy requirement of the application. After that, we check if the C rate is inside the proper limits, and if not, we run it again until we obtain the optimal cost. Finally, we had these results, and as you can see here on the left part, it will represent a full LTO battery pack, and in the right part, it will mean that the whole battery is NMC. And we have an optimal point just in the middle with these characteristics, okay? So we are going to combine both batteries, and in this case, we can see that we obtain optimal cost combining them. But we have to take into account that this result strongly depends on the cost of the batteries. If we change those costs, maybe this point can disappear or can move to another place. Here in the x-axis, as you can imagine, it will change depending on the power threshold that we apply to the power profile. And about the partial power converter. Well, first of all, I'm going to start with the architecture description, okay? Previously, it has been mentioned that the partial power concept manages only a small part of the power to control the full power of the application. But how can we do that? Okay, we have two main partial power architectures. The first one is the input parallel output series, and the other one is the input series output parallel. There are others, but those are the main ones. On the first one, we serialize the input with the output in the secondary part, and in the second one, we serialize the input in the output, but in the primary side, okay? And this is the characteristic curve of each concept. So in the y-axis, we have the partial power ratio, and in the x-axis, we have the voltage gain. The partial power ratio is a relationship between the power processed by the converter and the power that is transferred from the source to the load, okay? And the voltage gain will be the main relationship between the voltage of the load and the voltage of the source. In our case, the load will be the DC bus voltage, and the source will be the battery of a module. In this case, we use a battery with a smaller voltage compared to the DC bus voltage. So we are going to work always in boost mode. So in that case, what we want is to stay in this part, okay? And we want to be the converter near to zero. So between these two options, we chose this one, the input parallel output series, just to work in this upper part, okay? So, as I said, we work in boost mode, and we will have a battery together with the partial power converter and a lot of modules connected in series. And what happens if one of these modules fails? Well, the operating point will change. So we will move our converter from here to here. This means that we have to handle a higher voltage difference between the input and the output, okay? And consequently, we will have a less efficient working point because the power processed by the converter will be much higher in that case. But the system can continue working, so that's a good point. And how many modules do we have to put in series just to handle a one module failure? Well, we did an analysis, and as you can see, if one of the module fails, it will be different if we have 15 modules or if we have 5, for example. If we have only 5, the voltage difference that we have to handle will be much higher, and the power processed by the converter will be much higher as well. So the efficiency slows down. And for both batteries, of course. So as you can see here, if we choose a number from 15 to 20, it will be okay. So we can handle one module failure. And here are the simulation results for the partial power concept. Here we use a normal converter, normal isolated converter, the dual active bridge. Why this converter? Because we need an isolated converter in order to serialize the input with the output. Okay. Of course, doing that, we are going to break the galvanic isolation, but it's not a problem in this application. And here you have the different working points of this converter. In the y-axis, we have the voltage relationship between the input and the output. And in the x-axis, you have the angle for the phase shift of the converter. So controlling this angle, we can control the power transfer between the input and the output, okay? With the power profile of our application, we can see that we will be working in this part. If one of the module fails and we have to handle a bigger voltage difference between the input and the output, this point or these lines will be set in the upper part. What does it mean? The gray part will be the hard switching region of the converter, and the white part will be the zero voltage switching region. So much more efficient. As you can see here, the converter works most of the time in the soft switching region. So apart from the partial power processing, if it works in zero voltage switching, it becomes much more efficient, okay? And when the voltage difference is nearly the same between the input and the output, the power processed by the converter goes nearly direct from the input to the output without processing it. So the power losses are very close to zero. So as you can see here, both batteries work in soft switching mode most of the time, this part. The NMC works under soft switching for a longer period because this line is in a lower part, but this is because the voltage of the technology. And the hard switching occurs while the voltage is very low, and the switching losses are very low as well. So that's not a problem here. And about the experimental results, we took these different points, 4 points, to emulate the battery charging process, okay? So as you can see here, the battery, the module voltage will maintain the same in all the tests, and the battery voltage will be changing from a 0 state of charge to 100% state of charge, okay? So the power managed will increase as well. And as you can see here, we have the efficiency, and there's the optimal point, more or less, when the battery is in the 70% of state of charge. And why is that? Because when we arrive to this point, we have to reduce the power transferred by the converter. And if you remember, when the angle between the phase shift angle is close to 0, the power losses are increased because we enter the hard switching region, okay? And here you can see the effect on the temperature of the semiconductors. So in conclusion, the hybrid energy storage system solution can be an optimal solution, but take into account that it directly depends on the power sharing method and the power profile, and of course, the cell cost. The partial power converter can provide higher efficiencies because it only processes a small amount of the total power. The dual active bridge can work most of the time in soft switching mode. One module failure can be assumed without compromising the operation of the system, but it works better for small voltage differences. So if you have a very big difference between the input and the output in terms of voltage, maybe this is not your best option. And of course, we lose the galvanic isolation when we connect the input with the output. So if the galvanic isolation is a requirement, this is not your option. And that's it. If you have any question, I will be happy to answer it.
Is there any questions online maybe, or people from the audience? No? Yes, Julen?
Thank you for your very nice presentation. I've got a very simple question. I think it was slide 16, if I'm not mistaken, regarding the rule-based control. You said that you were using a power threshold method to choose or to select which system was providing the power on each moment. And I would like to ask you if you have tested this algorithm. I mean, is it able to provide with enough fastness that power to select which one is providing the power?
Yeah, it's a quite simple concept. You can program it with if else.
What I mean is that I guess that you want to supply a DC boost voltage, no? And in that case, if you have very fast load transients in the DC bus, maybe that voltage might be affected and its stability.
Yeah, but in that case, the high power battery will supply the peak power. So the high power battery is not limited. So it will supply the fast transient.
Okay, so you must have any other maybe grid forming or voltage source unit fixing the DC bus voltage, no?
There's a master unit that controls the voltage, and after it sends the order to the other strings to work in current mode.
Okay, thank you.
Okay. No questions online? Yes, sorry.
We discussed the sizing of the batteries, but how would you size the power of the partial power converter? Because it only has to process part of the power, and there are some failure mechanisms. Would you only dimension it for, let's say, 10% of the power of the application, or how do you deal with the uncertainty there?
Yeah. Wait a second. Okay, first of all, we have to know how many modules do we need here, okay? And we have to know which kPa do we need and which different voltage difference are we going to manage. Here, depending on the kPa, we can have some power losses, okay? So if we know the voltage difference between the input and the output, and we know the rated power, we are able to know how many losses are we going to have. So the main sizing is done with that criteria. And also we took into account what happens if one of the module fails. Okay, in that case, we have to recalculate everything and recalculate the power losses for that operational mode. So, I mean, if you know the voltage difference, you know the KPR, and you know how many losses are you going to have. Of course, you have to take into account that this part, the gray part, is going to be the hard switching part, and it's going to be the part where more losses are created in the switches. But at the same time, is the part with where the power transfer is nearly zero or very close to zero. So if you know the different working points, you can estimate the power losses. So you have to know the voltage and the operating point of the converter, and with that you can size it. I know if
yeah, so it's a trade-off between losses and power sizing, I guess.
Yeah,
which you then have to make.
Yeah.
Thank you.
I think it's related with the same question, because you say it is an increment of the power you need when failure.
Yeah.
So you need to oversize the converter, but you need to oversize in terms of only voltage or also the current.
Also the current, because the power transferred through the converter is higher. Wait a second. Okay. As you can see here, when one of the module fails, you move from a relationship between the input voltage and the output voltage. Imagine that you are here and your voltage relationship is close to 1, okay? And you are going to move to another point. So when you move to another point, the KPR, the relationship between the transfer power and the managed power, is less efficient. So the converter needs to handle a higher amount of power. So the losses are increased as well. I mean, when you perform the calculation of the losses for the transfer power, you take into account the current and the voltage difference. Yeah. Only the voltage difference. If the current is the same and the voltage difference is higher, the total amount of power that you have to handle is higher as well.
So you only rated for the difference in voltage because you will always have a fixed amount of current maximum.
Yeah.
So then you need to take care about the transformer and also the switches.
Yeah.
To be rated for a higher voltage only.
But also the operating point. If you start operating in the hard switching mode, the losses will increase as well.
Okay.
Yes. Okay. There is a question online.
There are some questions in the chat. My teacher is asking
not in this case, because the dual active bridge is the topology that we normally use and is isolated, bidirectional, and that's what we need. And it's a prototype. Maybe if we want to optimize that converter, we can use other topology with less amount of power switches. But for this case in particular, this was the solution that we chose.
Yes, I think that maybe the full power, we also took that into account, but you have to take also into account that the inductance is not inside the the transformer, and maybe the controller could be also more complex, but
what would suppose only assuming a single converter or failure in terms of
Sorry, can you repeat the question?
What would suppose if only we assume a single converter or cell failure in terms of reliability?
So you mean if one of the module fails, or if we use only one converter and a full battery stack?
A single converter.
Okay, if we use a single converter, that's the less reliable possibility, because we cannot assume a failure of the converter or a failure of any of the battery cells, because if something fails, everything is in series, so it's the less reliable option.
Okay, and it's asking also if how is all the structure protected?
Okay, apart from this, we have breakers and other stuff to protect the system. But inside the system, it should be enough with the converter.
Thank you.
okay. Is there any question? No? Okay, thank you very much, Eric.
Thank you to you.
Okay, we are running a little bit late, but we are going to continue with the next presentation. The next speaker is René Barrera Cárdenas, received the Bachelor of Science degree in Electronic Engineering and the Master of Science degree in Electrical Engineering from the Industrial University of Santander in Colombia in 2006 and 2010, respectively. He received the PhD degree from Norwegian University of Science and Technology in Trondheim, Norway in 2015. And he was a research fellow at University of Tsukuba in Japan from 2015 and 2016, and then was a researcher at University of Tsukuba also from 2016 to 2018. In 2018, he joined Sintef Energy in Trondheim, where he is currently a research scientist at the Energy Systems Department, and his research interests include modeling and optimization of power electronics and energy storage systems for electric transport applications. Okay, so René,
thank you.
Over to you.
Hello, everyone. So the presentation is try to introduce the modular multi-level converter topology and design algorithms we use for evaluation of this concept. Maybe all the other presentation has covered this background already, so I will go quickly through this. But as you already know, we have applications when we have a very high energy requirements and other applications with high power requirements. So the technology with high power and high energy gives me some margin where we cannot cover some other applications. We are in between. And if we try to cover that with a high energy, we will end up with solutions oversized in energy. And also, if we try to cover that with the power solutions, we will also oversize the solution. So if we have an hybrid solution with covers combined with these two, we can get the optimal combination. However, first we need to combine two different technologies here. So it is necessary new concepts coming.
And in new concepts, we have many design choices, which could be different trends from the standard choices we have for the standard battery systems. So it means we need to easily check an exploration of the new freedoms of degree that we came with the new topologies for the hybrid topologies. And then that's why we want to adapt one algorithm with a lot of flexibility to bring this kind of exploratory task. So the algorithm in general perhaps performs like this, where we try to map a design space. The design space is different design choices combination coming from the architecture we choose, the control we have, or also the components or the technology we have for this specific application. So we combine these possible design options in the design space, and then we try to map that design space in a design and performance space, which depends of the evaluation of a specific application and operating requirements. And then the exploration, it can be done by different optimizations techniques, multi-objective, like a single objective function, or different Pareto front techniques. And then we perform this search for all this design space. So the idea is try to map and try to see how the different performance behaves for a given application, constrained by a given selection of technology components and architecture. More in depth, the topology we are working with is the modular multi-level topology. This is the basic architecture. So we basically have a n number of strings, which are formed by a number of series connected modules. The modules can be, in principle, different each other, because the module itself, which is the core of this technology, is composed by two main parts: the energy storage part and the power flow part, which is realized by a DC-DC converter and use a half bridge. So the simplest converter we can have here. So then this gives the module the two main characteristics: to store energy and also to control the power we transfer from this energy storage. With this functionality, we can have more freedom here for the string. So when we have a number of modules, which not reflects exactly the total nominal voltage, it could be higher number of modules, because this converter allows to use bypass the converter, or use fully connect, or use regulate the voltage we want to get. So it means we can get this voltage as function of a given number of converters, given number of modules. Also, each string is independently of the other. So in principle, we can combine n different type of technologies of core cells. Here we are focusing two main, let's say, technologies: the high energy and the high power cells. But we can have more, and that is another flexibility. And other, we have this functionality also allows to have a high redundancy, high modularity, and and also we can have a special control here to define the power sharing between the different strings. So we can control easily the power going through the energy part of the system, or the high power part of the system. So thinking on that, so we try to identify what could be the main inputs for our problem, what could be in our case, the main outputs. So the main inputs is given a power profile, which could be combined with n time power series, depending on the use and the frequency we use in a year. Also, we have the technology specific for the core cell, which is the more important component in the system. So the energy or the power core cells. And also we have a general specification, like what are the nominal voltage we want or what are the desired lifetime. So this is a summary of the main characteristics in the global level. And what are our target is try to get a set of possible designs, which is defined by the different combination of high energy and high power sub-battery systems. And we take into account in that process different performance. So the cost as a first, maybe a most important here, but also the volume, mass, efficiency, and also itself the required installed energy and power capacity of the final solution. Because one thing is what we need to get the power profile, and other is what we need to install in the end, take into account that the combination of these two and the discrete of the problem. So we don't have a exact match with the profile. So this is in general how looks the algorithm. So first is a complex algorithm because the system is already complex. So if we try to do hybrids, it means two complex systems together. And but basically we can divide this in three parts. The first part is the power split. So how we share the power between the high energy and the high power subsystems. Then based on that shared power, we create sub profiles for the high power and the high energy. And then we try to check how much sizing the energy storage, which is more or less how much we need to install in capacity against the expected lifetime of our system, which is this part. And once we have these two parts running, which you see the first part is independently of what are the technology for the core cells you choose, and the sizing will depend on the technology of the core cells, but not of the topology of the system. But in the third part, we go to the specific design of the topology. In this case, it's a modular multi-level topology. And then we do the design for both parts of the system, so the high energy and the high power. We try to get a performance space for each subsystem and then combine in a global performance space. So it means we will try to check thousands and thousands of possibilities and try to bring these to specify or to try to see what are the best options. So I will go in deep of these three steps. The first is the power split. So I think you saw in the two previous presentations other methods for power split. We use a third method here. It's based on a low pass filter. I think these three methods will cover more or less what is now in the literature. The low pass filter is a method we choose because it's easy to implement in a real application in the power management system, and basically depends of a filter which taking the power required for the hybrid system. It's a low pass filter, so we take the we take a component for the low frequency of this power, and we limit that depending on the maximum power we want for the high energy. So we estimate how much power for the high energy and how much power for the high power batteries we need for a given profile. So basically we split this input profile in two profiles. Is that the main thing? So, but then we have two parameters here for this is operation, so discharging, but also we can have different parameters for charging. For the charging process, we have a similar part here, but also we need to take into account the actual state of charge of the batteries. So we try to prioritize the charging of one of the other system. But basically we have here 4 parameters, which could be, in principle, the low pass filter frequency could be the same. And here we have the maximum power for the energy and the maximum, discharge power, and here the charge power. for the energy batteries. We assume that that is a parameter instead of the high power, because the high power has more flexibility to supply the power. It's not imposing one limitation in our design. And from that, so from these three parameters, we choose to have two free parameters, and the third one, the charge power, is a function of these two free parameters because we need to balance the power profile. So we need to guarantee that all the power we discharge, we again charge in the charging time. So here's an example of how that performs. So the blue lines is the power profile, and we apply filter frequency, and with these parameters, this is an example for a given set of parameters. So if we apply for the low pass filter, the energy battery will have this requirement for power, and the power battery will have the blue one, the yellow one. And associated with that power, we will have a discharge and a charge on discharge energy profile. So it means this implicitly gives me how much power we need maximum for each subsystem and how much energy we need to supply for the application. But as I said before, this example was for a combination of two parameters, and the power profile is composed by n time series. And in principle, this parameter, this combination is not optimal it's not the same combination optimal for all the time series. So we can have this combination of parameters in a third dimension. So then basically we optimize the selection of these parameters for every time series because it's easy to implement. So it means these parameters or this algorithm is very easy to change. So we can change the mode depending on how we will use the vessel. So then this flexibility is easy to take into account here. Then once we have that, we have a performance space. So we define how we split the power. So then we will have for each high energy or high power subsystem, we will have a minimum usable energy we need. We have a maximum required continuous charge on discharge power. And also we have a estimation of how we will use this in a year, for example, through the annual energy throughput. So how much energy we need to take or how much cycles. But in this step, still we don't know about the cycles because we still not have a defined battery with the cells already. So we can estimate use the annual energy throughput. So with these four dimensions, we go to the next step. So this is a performance space for each subsystem. This is, for example, for a road ferry profile where we have two time series. One is more given for summer and the other more given for winter. And associated with these inputs, we have some energy requirements in the case of a monotype solution. When we go to the power split algorithm, we more or less do a mapping of this possible splitting in a multi-dimensional space. So for example, for the different splitting, we will have a different minimum energy for the high energy and high power system. So where basically the summation is always the same as the maximum here, which is 1.2 megawatt hour. So this combination, and there is some deviation depending on how much is limited the maximum power in each system. So also we can have the annual energy throughput for both and the power charging and discharging. So just for example, to see how easily this scale in the number of possibilities. Let's say we have these two profiles, and then we have a possible combination of this filter, let's say 20 different values from 0 to infinite. 0 means that we don't use the energy battery, and infinite means we don't use the power battery, and anything in between is a combination between high energy and high power. And we have 10 values for this one. So it means we have here 200 combinations, but this one is for each profile, 200. And then if we combine the two profile, it's a 14,000 combination. So which is a point here in this plot. So here we plot 14,000 possibilities. For that 14,000 possibilities, we need to estimate a model multi-level converter design space. Next, so we know what are the minimum requirements, but depending on how much use that system, we need to install more capacity. Why? Basically is because we have two limitations. One is the power. Normally we have a power ratio between power energy, or the C rate, also known. And also we have a limitation in the operating of the state of charge. Normally we don't use the full energy we have. We use a percentage. And also we have a degradation in the system. So with the time, in the beginning of the life, we have a full capacity where we only use a minimum energy for our application. But as the time passes, in the end of the design life, we will reduce the capacity we have, but the energy we need to use is the same as in the beginning. So then we need to take into account all these things to sizing adequately according to the application. So to know how much is the beginning of life capacity. So then this is the sizing algorithm basically. So once we define what are the core cells for high power and high energy, we can map, let's say, this graph here. With the minimum energy, we can map to the actual installed energy. So the blue line here shows what are the minimum energy in the previous plot. Here, the red line shows how much we need if we assume 80% of state of charge range. And this plot shows what is the actual energy we need to install, taking into account the degradation of the battery cells, which is the sizing is different depending on the performance of the battery cell itself. So these results are for these two battery cells, 155 ampere hour for the NMC high energy cell and 23 ampere hour for LTO high power cell. Maybe here, I think this is similar as the previous presenter, so I just go through this. And then once we have this, let's say, this space of possibilities, which is here, we can see first pre-estimation. So we define the cell cost, so we know how much will cost the cells of the system if we split in different ways. So more or less here, we already detect one area where it could be of interest for us, because if you normally see this system, more or less 80% of the total cost is the cost of the cells. So then already in this part, we have a pre-estimation of where could be the interest for us, even before go to the topology itself. And then we need to estimate the actual realization of these possibilities. And then we need to go to a more detailed modeling of the different components. And in this case, it's for the modular multi-level converter. We implement different models of the discrete components, going through modeling the inductor, the capacitors, the battery cell, the heat sinks, the power semiconductors, and how these discrete components influence the design of our topology. So the algorithm is divided in, so we always have this like kind of optimization loop where we have different freedom in the parameters. But here we have two main parts, which is related with the model design. So we need to specify the heat sink of the battery cells and the DC-DC converter for that battery cells we choose. So the main outputs for our algorithms are what are the nominal voltage of the string, what are the minimum energy to be installed, which is from the previous graph, and what are the maximum continuous charge and discharge power, which is linked with the current we need for a model, and of course the core cell. So we define the core cell, we define components technology with a method we call metaparametrization, which reduce the complexity of the discrete components evaluation and just refer to the technology performance itself. And then we sweep some parameters. The relevant parameters here are the number of series and parallel connected cells per module, and the maximum battery cell current utilization. So how much we will use the cells compare, how much we will use the cells compared with the total module current, and the number of modules per string, which also take into account the redundancy of the system. So with this freedom, we go to different sub-algorithms. So this is, for example, for the heat sink. So to define or to model things in more detail, we need to define, we need to go to the details itself. So we need to define a layout for the heat sink in order to model properly and to evaluate properly these kind of things. So we choose this kind of simple layout for the heat sink where we have the battery cells and some fins to transfer the thermal, the power, the temperature, sorry, the heat through the cool plates, which are in each side. And then we have some parameters here to optimize. So we can have different fin materials, we can have different fin thickness, we can have different cool plates properties. So we have, again, optimization here. So with many possibilities, which is inside of the module design algorithm. But at the same time, we have the DC-DC converter. So again, we need to go to the details. So the topology we choose is a half bridge, where we model the different components of the system. So we have a specific layout with a capacitor band, with a power switches for the upper and top switch. And we have the drivers and everything here. So the different model of the components are here. And then we have, again, a loop where we have different design parameters to optimize. For example, how many semiconductors we need for switch, or which type of heat sink, for example, air force or water cooled. And here we just filter this high performance space by select the cost, the minimum, by selection of the solution with the minimum cost, which give me a constrained dimensions of volume. This is an example of what are the parameters or what are the specifications we can have. So we have, for example, 1,000 volts stream voltage, a design life of 10 years. And then we have some characteristic of the cells, the high energy and high power. So if we define these two things, we have also some design constraints. It means our final designs will depend on what we choose here. Some of the things we consider is like not to have a very heavy modules. So we limit the maximum module weight or the maximum cell weight per module to 75 kilo. We have many parameters, but this is just to show that we should fix some of them because are too many dimensions, but still we have many freedoms to select. And also we should select a technology itself. So it means the semiconductor, there are many technologies, but for this application, we say, okay, it's a MOSFET because the voltage levels are more suitable for the MOSFET technology, but still we have different MOSFET devices. So the technique we use is only depending on the technology, but not of the discrete devices. The same for capacitors, inductors, heat sinks, and other components. And then we go from the main input is this power profile, for example, and then we go from here, and then we can map that for a performance space. So this is an example of how much installed energy and how much installed energy for high power and high energy we can split, and how much will be the cost of the discrete solution, the final solution. If you compare this with the previous plot for the energy sizing, the space is limited because we already filter. We are not interested in very high cost solution. We focus on the solutions close to the Pareto frontier here, and the realization of those solutions are limited by the discrete choices we do in the design. So this is, every point here is a actual design with a lot of details behind. We can plot the result ID, so we can plot the results in function of the performance indices. For example, the losses, expected losses against the cost, or the losses against the mass, or the cost against the volume. So there are different options because we already have all the data, so we just try to plot. And the way of doing that is that we don't not only focus on one solution, we focus on a set of solutions. For example, we can analyze all these solutions here to see what are the more common parameters of our system. So we get an idea of what could be the standard solution we can choose. This is more details. So for example, we have the minimum cost solution, but also we have a monotype solution. And if we compare, we can have a lot of details from that solution. So for example, how many parallel strings we need, how many modules in series, what are the number of redundant modules per string, how much will be the installed capacity of our system, or the power we install, or the module voltage, or the cost, and so on and so on. So there are many, many details here. The point here is that these details are for all the points. So we can do a analysis after we run the algorithm. And we can get a lot of information from this kind of algorithm. Also, we can do the same for different profiles. So this is for a raw ferry 1 in our project. And this is for a harbor 2. So different profiles will give me different performance space and different solutions. So we can compare how are they. For example, this is less prone to be a hybrid solution, but this has more pronounced solutions here for hybrid. So the hybridization for this profile is better than for this profile. Also, we can see the impact of the different cells technologies. So this is for this profile. This plot is for an NMC from rep for 155 ampere hour with some C rate characteristic and some number of cycles. And this one is for another NMC with the same LTO, I mean, for the same high power battery, but different energy batteries. And then this has higher number of cycles life, but less C rate and a smaller capacity per cell. And then we can have different performance space. So this is exactly the same profile, but we only change one component in the system, the battery, and we already get very different solution. This one has better performance for the hybrid. So it looks like one hybrid solution will be better with this technology than for this technology, for example. So conclusion, this methodology allows us for exploration of the design space to understand better a new topology like the modular multi-level converter. And then this brings like a interesting tool for preliminary design stage. So we can first try to see what could be the best range of parameters to reduce these problems to the next step, which is the standardization and production of these solutions. I think that's all. Thank you.
Okay. Thank you very much, René. Is there any question from the audience here? Okay. Thank you. Thank you very much. Very interesting presentations, very interesting questions also. I think, Jeroen, you maybe want to comment on something. It's clear that we need very powerful tools in order to develop all these analysis and optimizations.
Yes, indeed. Thank you. Thank you to all the presenters, and thank you for everyone asking questions in this first half of the program today. I think the fact that there are no questions is because everyone is very hungry. So I will not keep you waiting for much longer. But what I wanted to mention is that what you saw today and this morning, these three presentations were the three main concepts that in the Seabat project we investigated in more depth. So the discrete hybrid topology, the partial power converter, and then this module level converter topology. You saw an overarching presentation on what the topologies can do on the different parameters that are taken into account and so on. In our deliverables and in the project, we performed an in-depth analysis on all different load cycles that we considered on various KPIs that were shown earlier and so on. And we have compared these three. And in our project, we will continue with the last presented topology. So this module level converter topology is the one that we will use for the remainder of the project and that we will bring into practice. So the two others remain an academically very interesting concept that will not be pursued further in the context of Seabat because we can only choose one, of course. So in the future, you may expect more results and more in-depth information about this technology. That's what I wanted to inform you about. Back to you, Agini.
Okay, thank you. Good, so let's take a lunch break. The lunch is also being served in the hall. And well, we are running late, but I know maybe we can meet again here at 1:30, if it's okay for you. Yes, we will also want to take a family photo, all of us here. So maybe we will do it now, and then you can have lunch. Okay, thank you. Buah, se nos ha ido de madre. Se nos ha ido de madre. Pues no sé si decir 1 hora, 45 minutos, para comer. Sí. A mí que alguien me quede esto, por favor. ¿Qué? Muy bien. Vale, sí. Bueno, y si no entras, bueno. Si no entras cuando quieras, no te preocupes. Pues fuera, vale. Supuestamente ahí se iba a estar a las 12 ahí fuera, pero como vamos con retraso en el grupo. Bye.
I need a helping hand. Like a baby, cried like a baby. All night long, Well, that 61 highway is the loneliest road that I know. Well, that 61 highway is the loneliest road that I know. She run from New York City, run right by my baby's door. Wow, some people say city Greyhound buses, they don't run. You know, some people say that city Greyhound buses, they don't run. Wow, gonna go to West Memphis, baby. Look down Highway 61. Please see somebody for me. I said, please see somebody for me. Ah, see my baby. Tell her she's all right with me. Mr. Merrick Rock Patterson. If I should happen to die, babe, honey, for you think my time has come. If I should happen to die, baby, honey, for you think my time has come. I want you to bury my body right down there by Highway 61.
Let me tell you a story about a little girl I know. When she walks into a room, you know she steals the show. She's crazy. And it's more than I can't stand. I'm just crazy about that woman. And she's just crazy about this man. She wakes me every morning with that tender loving touch. Some fools don't get enough, but she just loves me too much. She's crazy. And it's more than I can stand. I'm just crazy about that woman. And she's just crazy about this man. I'll sing it. She always wants me round when I just ain't got no time. But you know she's got these little ways to make me wanna change my mind. She's crazy. And it's more than I can stand. I'm just crazy about that woman, and she's just crazy about this man. It's a lonely world. Everybody tries to hide. It's a lonely world. Everybody tries to hide. But you're all alone. All you do is fight. People live their lives with a rule to satisfy. People live their lives with a rule to satisfy. But nobody sees you crying. Nobody knows how hard you try. send me an angel. I need some helping hand. Would you send me an angel? Yes, I need some helping hand. Can't take this by myself. Can't get along, 'cause I just can't stay. believe you. You can say I told you so. And if I ever hurt you, you know I hurt myself as well. Is there any way for a man to carry on? Do you think I want my love more? Said I love you more than you ever know. More than you when I wasn't making too much money. You know where my paycheck went. I put it on to you, baby. I never spent one way and say. Is there any way for a man to carry on? Do you think I want my love alone? Said I love you more than you'll ever know. More than you'll ever know. I'm not trying to be just any kind of man. No, I ain't. I'm just trying to be somebody. Yeah. You can love, trust, and understand. I know that I can be part of you that no one else can see. Yeah. I gotta hear you say, I got to hear you say that it's alright. I'm only flesh and blood. I can be anything you demand. I can be king of everything. Oh, just one tight grin on say. Is there my love, oh Lord. Said I love you more than you ever know. Say I love you. I love you. I love you, baby. I don't want nobody else. Need nobody else. I just want you, baby, for myself. Yes, I do. Woman, I want to ask you, why'd you do that anyway? And I thought things were fine. Just yesterday, woman, you've got to tell me. Oh, yeah. You know, I can't spend one more sleeping in this lonely bed. Now lay here thinking about what you do. You know, I know it was wrong, baby, but I'm ready to forgive. Baby, you've got to tell me what's going through your head. No, I can't spend one more night. Ooh, sleeping in the bed. baby. What's it gonna be? You're gonna come back home, Lord, and stay with me. Oh, have I got to get myself another room? You know, I can't spend long. No, I can't spend all night.
Walk the streets on my mind. Doesn't it do strong around fine? Well, my baby, what is wrong? Someone told me you wanna get your baby back home. Stop crying. Yeah, yeah. Stop crying. You have someone new, but I'm still in love with you. That's why I'm crying. Went to some places where to go. Friends or two, don't come around no more. Well, the island, yes, I see. I saw that same moment that taken you away from me. Stop crying. Stop crying. You have someone new, but I'm still in love with you. That's why I'm crying. is on your mind. But let me tell you, darling, I got to stop right. Well, beyond us, that's what I see. I saw that same woman. They're taking you away from me. Start crying. Yeah. Start crying. You have someone new, but I'm still in love with you. That's why I'm crying.
Okay, so welcome again. I hope you enjoyed the rant. We are going to continue with this with the last part of the workshop, and well, our next speaker is Amaya from Ikerlan. Amaya López de Heredia obtained her engineer and PhD degrees in electrical engineering from Institut National Polytechnique de Grenoble in France in 2003 and 2006 respectively. And since then, she's working at Power Electronics Department in Ikerlan, where she manages industrial and research projects. Her main fields of research are the advanced control of power electronic converters for railway transport, electromobility, grid-connected and renewable applications. Okay, so Amaya, the floor is yours.
Thank you very much, Argine. Good afternoon, everybody. I will speak about the wide bandgap semiconductors for power electronic applications. I will start my talk with a brief introduction about Ikerlan and Seabat project. Then I will talk about new wide bandgap semiconductors and experiences developed at Ikerlan, and then to finalize with some conclusions. Ikerlan is a private, non-for-profit technological research center located with main headquarters are in Mondragon, with 45 kilometers by car from here. But Ikerlan also has another building in Orona Campus Ideo here in the next building. So after the workshop, we can visit also Ikerlan facilities. Ikerlan is also a member of BAG Research Technology Alliance. And even if our final goal is to transfer technology to our industrial clients, we also collaborate with leading technological research centers and universities in order to improve our knowledge. No? So different European projects like Seabat project. Ikerlan is a work package for leader in Seabat projects or components development. We have to design and develop components for the modular and flexible hybrid battery system towards low cost. No? So we have to design the BMS, the DC converter, the cooling system, the mechanical housing, system protection, etc. And this currently this work package 4 is still in an early state of design. We have the milestone next year in May 2023, where all the components should be built. So for the next workshop, maybe in Polito, we can explain a lot of information about work package 4. But now what we have now is the topology has been already chosen, the modular multi-level topology that has already been explained with my colleagues. So the prototype that will be built in Seabat project will have 2 modules connected in series to a 1 kilovolt DC bus. We'll have 2 strings of 155 amps. So its module, its DC converter should be around 100 volts and 155 amps. So Ikerlan, who is involved in the design of this DC converter, has been analyzed different semiconductors possibility. And if we analyze GaN devices, they have, but in this case, we need very, very high current. So a lot of devices will be needed in parallel. So it's a very expensive solution. We also consider devices, but as we have very low voltages, it's not appropriate for this application. So we decided that silicon devices had the lower cost and with enough performances, so it will be the best balance option for this project. No? So even if in Seabat project we are going to use silicon devices for the DC converter, during the last year, more and more in more and more applications, silicon wide bandgap semiconductors are being used for different power electronic applications. Ikerlan has a lot of experience developing this type of converter. So in the next slides, I will present some top information about this topic. When we design a converter, we have the different vectors that want to be optimized. It can be to minimize the losses, the weight, the volume, the cost, even the time to market. So depending on the application, we prioritize which of the vector is going to be improved. Regarding the other figure about the performance of the different technologies, during the last decade, we can see that for every limit, there was another technology or another material that appears to surpass these limits. No? So we can see that, for example, at the beginning of the 21st century, we have the silicon superjunction technology that improved the limit of silicon devices. Then when silicon carbide devices appeared, this in performance limit was even improved more. And in the last decade with GaN materials, this performance indicator has been even improved more. No? So if we want to compare different wide bandgap semiconductors like silicon carbide or gallium nitride with the classical silicon devices, we usually use these 4 figures of merit about the conduction resistance, the output charge, the gate charge, and the thermal characteristics. For this comparison that we are going to present in the next slides, we have to say that GaN devices can be divided into different types of groups depending on the voltage. We will say that low and medium voltage devices will be compared with silicon MOSFET devices, and medium and high voltage devices will be compared with silicon superjunction or silicon carbide devices. Also, in these medium voltage, high voltage GaN devices, we have to say that only 650 volts devices have been analyzed because in 900 volt devices are still in an early stage of the development. So if we compare GaN and SiC devices with respect to the solution, we have the different operation voltage. Regarding the figure, we can see that the conduction resistance is is lower in case of the GaN devices and similar in the case of the silicon devices. In both cases, we have fewer switching losses and very bad recovery charge from both cases. In the case of the GaN devices, this is the figure where more difference can be found because GaN devices require very low gate driver charge. And with this advantage, we can see that silicon carbide and GaN devices allow switching at very high frequencies with similar losses to the silicon devices. But of course, it also have some disadvantages. The most important one regarding the The GAN devices is the low gate driver voltage, which can cause a false turn-off, so it's very challenging for the design. In both cases, we have a very poor quality diodes, so we need or minimize test times for an anti-parallel silicon carbide diode to minimize losses. In the case of the GaN devices, as we said before, we had a very less thermal capability. And one disadvantage of both systems is that we have very high switching speed. So we have EMI problems, degradation insulation, also of the bearings in case of the inverters and the motors. Regarding the reliability, we can say that GaN is quite a mature technology currently, and SiC devices, even they have a better reliability, this is still to be proven. And finally, regarding the cost, at present, GaN devices are 4 times more expensive than silicon devices, but expectation of a considerable price reduction is expected, no? When dedicated production lines will be launched. However, in the case of the silicon carbide devices, the cost is 3 times higher for discrete elements and even 10 times higher for modules or high voltage with high voltage. And even if a download is expected, they will not reach silicon prices. Regarding the potential GaN applications, at present we have a universal new charger, GaN-based, with very small size. We also have a Corsair power supply units for computer. Even for automotive application, we have an onboard charger of 6.6 kilowatt, and also Yaskawa PV inverter of 3 kilowatt. But even if we have these examples, the potential application are still not clear. This is different for the case of SiC application, where quite commercial converters can be found with silicon carbide devices in photovoltaic application, in railway application, also for a mobility, industrial application, and more also for connected substation, aeronautics, etc. So now I will present a little bit the experiences developed at Ikerlan for different projects. Ikerlan started working with GaN devices in 2015 with power-based project, where the task of Ikerlan was to validate the components developed within the project. So we evaluate different cooling solutions. Top from the bottom, as we said, the thermal solution is very complex in these GaN devices. We built a 4 kilowatt converter and a multi-level modular converter. We test soft switching and hard switching analysis, also single solution or parallel devices in order to improve the current of the system. And in off cases, we achieve very high efficiencies. Then we work also in other project, a cost project. In this case, also is hybridization about high power and high energy system, but for an electric vehicle application. So the role of Ikerlan in this project was to develop this DC-DC converter here between the both batteries. It was a low voltage converter, 48 volts and 204 kilowatts converter. And here this was a very integrated and compact solution that in the whole system was considered here. No? This is only the DC converter. So a comparison was carried out, no? Comparison the silicon-based solution and the gas-based solution, and as it can be seen, losses, volume, weight, everything was reduced considerably. Another European project that Ikerlan has been working on is Ultimate GaN. It's also an Excel project. Here, the objective was to develop a bidirectional domestic 3.3 kilowatt wireless charger. Here, the challenge was to do a low profile design in order to wall box and decoy in a unique housing, that this one. So this is all the charger. Also to increase the power density using a novel topology, and this converter was experimentally validated with a charging distance of 100 millimeters, a switching frequency of 85 kilohertz, and achieving a 96% of efficiency in the back-to-back operation. So regarding SiC designs of converters, Ikerlan started in 2013 developing the first very low power converter, continue developing some drivers because there were no commercial available drivers at that moment. Start developing converters with more power, 50, 100 kilohertz, also 225, with hybrid silicon carbide devices, then full SiC. And in 5 years, we have already a prototype running in a real application. We continue working in different applications for PV, induction, kitchen, also analyzing different drivers. We work a lot in traction inverters, as we'll see after. So in 9 years, we develop a very wide power range of different silicon carbide converters. Now I will explain some of these examples more in detail through different projects. We work in reaction project. It's also an Excel project where the objective was to develop the European silicon carbide 8-inch pilot line. So Ikerlan in this case also tested some components developed during the project. We developed a three-phase two-level SiC inverter, 100 kilowatt, switching frequency of 20 kilohertz, and a target efficiency of 98%. Now we are experimentally evaluating this converter. This is the first figures that we have some weeks ago, or the thermal characteristic of the converter. And now we are working on a 20 kilowatt isolated DC charger, which is in the design phase and will be tested during the next months. Another project is the Research for Rail. It's a Shift-to-Rail project where we analyze these silicon carbide devices for dynamic inductive power transfer in railway application. So the first task of the project was to make a trade-off between this dynamic charger and the onboard energy storage unit, comparing different battery technologies and different charging systems. We also characterize the different silicon carbide devices, 1.2, 1.7, 3.3 kilowatt in the zero voltage switch to see what has the lowest switching losses in order to develop our inductor power transfer system. And now we are in this phase, sites in this converter. The objective is to have higher efficiency and lower size than classical silicon-based solutions. And finally, the last project is Seabat that started 10 days ago. Ikerlan is going to lead this project, and it haven't even a logo yet. So in this case, it's also for the maritime application. We will develop in the project. We'll develop a fast modular multi-megawatt charger for maritime application. The objective of this project is to improve efficiency by 20%, to develop a 50 compact charger, also to reduce losses 50%, and reduce the operation and maintenance cost 20%. So in this project, there is a task where we are going to analyze if SiC devices will be the best option for develop this charger. We'll develop some prototypes in some years, so we'll see if finally this charger will use silicon carbide devices or not. Here we have some slides about the industrial projects we developed with Ikerlan, with Cap Power and Automation, which is a company based on the development of power electronic devices for railway application. It is also located here in San Sebastian, and I know that some people from this company are also in this workshop, and also Euskotren, which is the Basque railway operator. So we developed a SiC hybrid solution for 600 kilowatt inverter, and after testing in our labs, it was installed in September 2015. So it was replaced a silicon-based converter with this silicon carbide converter. So we could compare loss reduction up to 50% and energy saving up to 3%. Then we developed the full SiC solution. We tested in Ikerlan laboratory, and last year it was installed in the train and is currently running. So if you came from Bilbao to San Sebastian by train, maybe you can have the chance to be powered by a silicon carbide converter. So in this case, the volume reduction was around 40%, the weight reduction about 25%, and the losses reduction about 65%. Here it's important to say that the cost of this converter was much higher due to, at present, silicon carbide devices price is still quite high. So to finish my talk, some conclusions. We can say that every wideband semiconductor has its optimal scope for work. GaN devices will be oriented for low voltage and power, smooth switching and high frequency, while silicon carbide devices are more oriented for high voltages and hard switching. While GaN technology allows to raise switching frequencies well above that silicon allows, with the minimization of the volume and the weight of passive components, which is quite important for a lot of applications, minimizes losses in the converter and also for the cooling system, minimize acoustic noise, and improve the needs to be evaluated at a system level, not only a converter level. High current SiC product range are already available, discrete and modules. So starting to produce serial devices, but still the price is very high. Silicon carbide is promising technology in terms of reliability, and GaN can still be considered immature for mass production. And GaN's manufacturing method promises significant price drop. And regarding the research, which Hernani is involving now, so on the impact of rapid switching, so we have to investigate on the degradation of magnetic components insulation due to high DVDT, and also on the EMI effects and filters to comply with the MNC regulations. That's from my side. Thank you very much. And if you have any question.
Any question? Alessandro? Yes.
Thank you, Maya, for your quite interesting presentation. You mentioned in one of the first slides and also at the end the matter of reliability and failure rate, or as I would call that, the mean time between failures, which is quite important for all the components, at least from the perspective of the class societies, to make sure that the system will work. So how did you measure or evaluate or test the reliability of the system? I'm telling you that because I recall in the past asking the same question to a big manufacturer that was providing the converter system for the propulsion electric motors or a big ship, and say, so what is the failure rate of your system? And he replied, well, it never breaks. So I would like to understand something that is less commercial and more to the point, because a single element can compromise a system that will compromise the ship. So what are you doing, or what is possible to do in terms of a measurement of the reliability? Thank you.
In our case, we don't work especially in reliability issues. We develop prototypes to make the concept, but after to become a product, of course, there is another puzzle that the companies have to deal with this. But of course, silicon carbide devices appear as to be unreliable, but it's not easy to prove this concept, not at least at prototype level. When we are working with GaN devices, we realized that they are not reliable at all, because even in laboratory tests, they broke. So it was quite easy to prove that they were not reliable at all. But in case of C devices, at least in laboratory level, we have good results and no problems. But we know that it's something that is very important, as you say, because of the price of the devices, and in order to be cost effective, it must be assured. But it's something that Kerlan, even if it has some research about PhD students about in this topic, in this project, and we are evaluating the reliability. As I say, the converter is still in the train. Every month we have data from this train, so we are knowing that this converter is working very well. So we are expecting that even maybe in some times we will have some failures and some, but at the moment is what the only prototype that we have running in a real application, and having mesh data every month. And up to now, the converter, as far as I know, is running quite well.
Ramon.
Yes.
Yes, just to say something more about this, it's really difficult to have some theoretical analysis because the manufacturers don't give you the data. And I think that is because they have some tests done, but they don't have the real data. They don't still have the real data. And I'm talking about silicon carbide. When we talk about the GaN devices, they don't have. In this project, for example, in the Ultimate GaN project, for example, there is a work package regarding these reliability issues, and we are different partners and we are doing different kind of accelerated tests, but we don't have still data.
Thank you, Luis.
Hi, I'm David Marcos, and I am also a colleague of Amaya, and I would like also to complement her answer. When you're dealing with reliability, there are two approaches in this case. The first one is to actually calculate and theoretically obtain the time to failure or the failure rate, which in this case, as also my colleague Luis Mir said, you need the data from the manufacturer in that case, because the manufacturer has to actually run a lot of tests and a lot of destructive or temperature tests in that case. And the other one is, of course, to actually run several tests over the final prototype and everything, but that of course has a great cost. And here in Netherlands, although we usually do those tests, those calculations for the final reliability, we do not normally test against the reliability of the final product.
Okay, thank you. Is there any question online? No? Okay. Gerard, yes, please.
Yes, to wrap up on the topic of reliability at Founders Make, we have noticed the same thing, that it's extremely difficult to find numbers. So now our colleagues of the University of Brussels have gone about and purchased infrastructure to do the tests that the manufacturer should have done in the first place to gather all the data. So I concur with the colleagues that it's about the data, and yeah, if you cannot find it in a data sheet, you need to generate it yourself. I also had a question with regards to the future trends. So you indicated some future trends with regards to price. The price of GaN is supposed to come down, and also that of silicon carbide, but it will not to the extent that it should. Are there other important trends that you see in wide bandgap semiconductors? I see the voltage levels of the silicon carbide rising. Is the same trend happening for GaN, or are there other things happening in the future that we should be aware about?
But our experience is that GaN devices will be regarded for low voltage applications, and even if there are some research also for inverter, for electric vehicle applications, but it will not be clear that will be. I think that GaN is for low voltage, low power, because and SiC will have the high power, high voltage applications. And because of the price, we know that we have also the problems with the chips, and is everything. We expect that the price will go down as far as possible, as was expected in the beginning, no? But it's something that they have improving efficiency, the reducing volume and weight. It's very important for our applications that this like our application or the mobility or the volume and it's very important, no? And the efficiency. So we think that more and more we'll see power electronic converters with at least SiC devices. GaN, it will take more time, but SiC devices are already in the market. So
And perhaps we'll see more improvements from the module level and the system level than the real materials themselves.
Yes, is that in the case of the SiC devices, that's why we say we don't have to focus on the converter, also at system level, because this improvement in the efficiency, in the switching frequency, you can improve for the control, for the passive element, for the cooling system. So you have to take the system as a whole. No? The improvement is bigger if you consider not only the volume reduction of the converter, no? But it's something that is clear, no? But it's quite bigger the impact of these devices in the whole system, at least in some applications.
Okay, lots of work for Ikelan remaining. Thanks.
Yes, please.
Hello, thank you, Amaya, for the nice presentation. I was wondering that you mentioned the system level impact, and if that analysis is already done for the train application that you have with silicon carbide, and is included in the price difference that you mentioned in the last slides.
No,
thank you.
You are asking for that, I guess.
Yeah.
What we did here is to change only the converter and the passive element around the converter, but of course, in this case, the control, for example, was not changed. It's the original control that has the silicon converter. So we know that as now we are switching faster, we can improve the control, and it's something that we are working on. But it's in the trend that is running is not changed, the control.
And regarding the losses and the cooling system, is the cooling system price reduction also included in that cost?
I am not sure because yes, I think that it's everything inside.
Okay, thank you. Thank you very much.
Later on in the labs tour, we will have the opportunity to see one of our prototypes. It's a SiC converter, a SiC-based converter also.
Yes, just to say a little bit more about this question. We are also analyzing the improvement of other components like the machines, for example. We think that improving also the machines and the control strategy for these machines, we can also improve a lot more the efficiency. You've seen in the previous one that the efficiency is improved between 1.4 or 1.5 and 3%, depending on the yes. And we think that we can improve even 4 points more using new machines designed and oriented to this silicon carbide way of working or these things. But it still has to work a lot in this part of which is the effect of DVDTs on the machine, on the isolation of the machine, and all these things. So
very degradation.
Is there any other question? Okay, thank you, Amaya. Okay, so let's move on to the next presentation. Our next speaker is Eva from Fraunhofer. Eva studied mechanical engineering at Technical University of Darmstadt. She works since 2009 at Fraunhofer LBF, and her focus of work is the design of structural battery components and the simulation of mechanical systems for finite element and multibody analysis. The activities where she is involved include research projects funded by the German government and the European Union. And in 2018, she received an award for excellence from the Fraunhofer Society for her technical and management skills. So Eva, over to you.
Thank you very much for your introduction. And hello and welcome, everyone. Today I want to talk about lithium-ion battery systems and from the mechanical point of view. my presentation is divided in 4 parts. First, I want to tell something about the basics of lithium-ion technology. Then I will give you a brief overview of the architecture. Then I will show you some general requirements for the mechanical parts. And then I will give you a quick overview of the process of the mechanical design and some points on the validation process. Yes, lithium is an alkali metal, and it has the most negative electrical potential and also the lowest density of the metals, and therefore it's the perfect solution for battery systems. You can buy this technology since the early 19th, and this is quite a new technology compared to combustion engines, for example. Yeah, so you can find it on vehicles on the street, you can find it on your smartphone, you can find it on power tools for your home constructions, and also you will find it on ferries and harbor tugs, for example. Yeah, they have a lot of advantages. As I mentioned, the high energy density, they have a quite high cycle stability, and also a low self-discharge rate. But there are also some disadvantages, some challenges on this technology. The first one is the temperature sensitivity, which has an impact on your mechanical design. I think you know the range where it's the best to operate such cells. And when you do not have the ideal temperature, you will lose your driving range. You will have cells with a quick aging, and you can run into safety problems when you don't obtain the right temperature. And the most important point, and the most challenge is the point with the fire characteristics of these cells. Yeah, lithium is flammable, and unfortunately, you cannot distinguish when a cell is burning. The only point you can do is to reduce the effects on the other cells. Yeah, and this is the so-called thermal runaway. I think all of you know what a thermal runaway is, right? So I can skip the details here. Yeah, okay, good. There are 2 main paths of it. You can have it an event from cell internal or cell external. A lot of points can already be done or be saved by the cell manufacturer itself. But you can also, you have to do a lot from the electrical point of view. So your management system is quite important, and also from the thermal point of view, and also, of course, from the mechanical point of view, you have to do a lot of effort that the cell is safe inside the system. There are 3 important formats available on the market, which are used in all the different applications. You can have the cylindrical cell, the prismatic cells, and the pouch cells. The button cells, the third version, is unusual. It's more used in Bluetooth applications, for example. The cylindrical cell is the most common type due to the fact that it's used on the consumer electronic market. It's quite cheap to produce, and it also has a good mechanical strength due to the shape and the stable kern. But it has a poor heat dissipation, and it's not that ideal for packaging. Yeah. The prismatic cell, from the mechanical point of view, is my preferred one. It's quite good as it's rectangular and a flat shape. It's perfect for packaging, and it's also have a better heat dissipation. Yes, and the pouch cell is a different version of the prismatic cell. It's missing the solid housing. It's packed in a foil. And yeah, it has good cooling properties and good heat dissipation. And it's quite cheap in production. But the main disadvantages is from the mechanical point of view, it's too weak and you have to make a lot of efforts to put these cells inside the casing that they are safe. Yeah. In Seabat, as you already know, we choose prismatic cells. I'm quite happy about this, but they will have different dimensions. This will be one of our challenges in Seabat because we want to pack them in one identical housing. So I hope we will manage this in a project. Yeah. As one cell is not enough to get on your voltage level and the energy density, energy content, they are packed in serial and parallel connections. Then the next level of system could be a submodule or a module. There are different ways of defining this. For example, from the BMS architecture or from the mechanical point of view. Sometimes you have in project difficulties to get the same definition of what is a module. And yeah. And then you have the next level, your battery system itself. It contains of a lot of different components, which all has to be fixed inside and find a place inside your housing. Yeah. Yeah, I brought you some examples. These are from the automotive sector, but the main point is that you have a broad possibility of the design. Every system looks different. This example here, both systems have the same energy content, but they use different cell formats. So the lower one here, the prismatic one, and here the cylindrical one, the upper one. Fun fact, the cell race is almost the same, but as I mentioned before, it's not that funny to integrate prismatic round cells. It's almost a factor of 2 of your amount of cells. And yeah, the system here will end up with 86 modules, and this here one with 16. This system here is semi-open housing, which later on the next level on this battery system got a housing which was closed. This module here is completely closed by itself, so you can use it as standalone. Yeah. So, the architecture from the mechanical point of view. You have a lot of different components, but you can divide it in 3 main domains. So the mechanical domain, the thermal domain, and the electrical domain. The electrical is here marked in yellow and red, the mechanical in green, and the thermal one in blue. And for sure, you need then some interfaces yeah, the electrical domain covers the high voltage and the low voltage current, the communication, and the job is to detect critical conditions and to lead to appropriate actions, mainly due to the battery management system. And to do so, there are needed a lot of components like fuses, sensors, contactors, a lot of cables and wiring. Yeah. Then the thermal domain, the only job is to have a good thermal condition for the ideal charge and discharge behavior. There are systems on the market which have no active system at all. And there are systems on the market which has to be heated also. So we are not talking about only cooling. There are also the need, maybe depending on your application, of heating your system. What is the job of the mechanical domain? You have to integrate a lot of things. Sometimes you have not enough space. Then you have to fix them. And the other job is to protect the cells, so everything what is inside your housing. And you also have to protect the person who is operating with this system. And then you have to fix the battery system on a ship, for example. As we talk about chip application, one of the important things here on the mechanical side, that is a good corrosion resistance. So every screw has to be taken into account here. And there is the part of the mechanical and thermal loads on the components. And therefore, all the mechanical properties has to be designed for the mechanical load profile. So we're talking here about vibration and shock. Due to the time, I have only some slides here on the components, on the architecture. For example, the cell orientation can be different. And this can be restricted by your cell manufacturer. Some cells, for example, tend to leak when they are put upside down in the system. And there can be a recommendation from the manufacturer that the venting valve is not put in this direction where the maximum acceleration is expected, in case, for example, of a crash event. Then you have a lot of possibilities to range the cells. You can have a lot of lines, you can have different levels in your system. This is strongly depending on your volume, which is available, and in addition of the requirement of accessibility. The next point is, how do we fix the cells? There are different approaches. You can completely capture your cells, or your stack, or your module, however you define this, this amount of cells, or you just use a retainer solution. This is quite a good lightweight design. It's called cell to pack design. The other version would be the module to pack design. Or you can just glue them together. I have seen this also, but this is quite hard when you're thinking about recycling. This is a no-go because you have to take them and to throw the cells away. Yeah. The material used for the cell fixation, there's a broad spectrum of this. Sometimes, always, you have also a hybrid solution here. The most important point is the materials, the mechanical strength, and from the safety point of view, it has to be non-conductive, and for the marine application, non-flammable. So, yeah. Here some examples on the thermal domain. The thermal, at least when it's active system inside your battery system, it has quite large impact on your packaging and assembly process and so on. There are systems with no active or with no cooling or heating at all. but as we know, it's better for your aging and also for your safety when you have a cooling on board. Yeah. There are quite a lot of possibilities of the medium or media. You can have it air cooled, you can have a liquid, so water glycol system, you can have a refrigerant system, so this would be the gas version. You can also have PCM and heat pipes inside the system, but this is quite a new technology and not that commonly used. And also here the possibilities of the surface where the cooling plate, for example, or the fins are located. Tap cooling and immersion cooling is also quite unusual and costly also because it's quite new. Yeah. As I mentioned before, the fire problem, the fire challenges is quite important on your battery system, and there are different ways to do so. You can have on cell level your first possibilities to protect the cells, or you have it on system level. For example, on cell level, you can put some pads between the cells, or you work with distance between them, but distance will have an impact on your energy density because you have that volume in your battery system. There's also the possibility of coating the cells with some special material. And I haven't seen it so far, but the colleagues, I think it was from Rina, told us there's a possibility to use intumescent material to protect the system. It's used, I know it from the construction of buildings, that you have some material which will expand when there is the heat. Yeah, and quite broad, you can add some additive into your plastic components, the flame retardants. I think we will hear something from Bernd later on this topic. Yeah. On the system level, you have a lot of possibilities. For sure, you can put the flame retardants on the housing itself. Active cooling is also a good solution, that you cool down the environment and also the neighbor cells to protect them from the thermal runaway. Yes, so far, I think this was the most important points. Let's have a quick overview, a quick look on the requirements. So far as we know now, for the maritime application, we can, it's will be the case that the battery space where the system is located will be ventilated and cooled. So it will, well, it's quite unusual that you put your battery directly on the deck, on open sun and so on. And this space will dedicate it only for the battery system. And normally it's unintended. Yeah. We already saw this number of the lifetime. The minimum requirement is 10 years, and we tend to go further. So yeah, this will show the project then later, at least for the mechanical components. Yeah. The cells has to be assembled in suitable crates and trays. So for me, it's the housing, the module housing or the system housing, equipped with handles, because you have to lift them from the harbor inside the ship and maybe you have to do some other work inside the ship, and it's the best solution to have here some points to attach the crane, for example. Because we are talking about around about 100 kilograms, maybe more. I don't know the number now, but at least 100 kilograms for one module in Seabat. For sure, the battery boxes or the module has to be fixed inside the ship, and it has to withstand the force during heavy sea. Okay, here's the question: what is heavy sea? This is strongly depending on the ship itself, but we have to take a look in the project what this means, and to get a design ready for a broad spectrum of applications. And we talk not only about accelerations, we also have to talk about inclinations. So this is not that important in the automotive sector, but I think the ship is quite more moving, and I think the acceleration will be maybe a bit less, but the inclination is a point for the mechanical here. And yeah, the goal is for sure that it has the system that to withstand the vibration without any rupture, electrolyte leakage, and fire and explosion. From the material point of view, it has to be the housing and the cell holder, as I mentioned before, flame retardant material, according to this international standard here. And we should have an IP rating of minimum 44. Preferred is the IP rating of 67. This is quite the same like the automotive sector. Yeah, the maximum possible would be 69. And due to the safety, it is needed to have a pressure relief function on each module to prevent overpressure and the explosion of your module. Here are the challenges that we have to look into detail. The question is, or the recommendation is, to have a cell level thermal runaway propagation. And the other challenge will be the access for the maintenance and replacement on cell level from the top and the side. This could be quite challenging, but we will check this and do our best here, that the cells each cell can be replaced if it's needed, because the ship hopefully will run longer than the cell. Yeah. So this is the last part of the presentation, the mechanical design and validation. Currently, we are around about in this area here on Seabat. We started with the requirements. There were a lot of general requirements, some detailed requirements like the IP classification. There are requirements from ship to the battery system, but for sure there will also be some requirements from the battery system to the ship. Yeah, we have now a clear view of the main components of the possible architecture of the system. Then we will go to the design part. First, there will be a preliminary design and then a final design accompanied with the FE simulation. And then finally, we will get to our hardware, to the prototypes and so on. And then the last step will be the validation. You already can do the validation on material level quite early in the project. And the last one will be on system level then. Here's a list from the mechanical domain. In the sense, also some requirements we have to fit. The impact test, this is more or less on cell level, as I understood, on the standard which is mentioned here. there has to be shock and vibration tests, a drop test, the IP verification, yeah, and the propagation test, and the gas analysis according to some rules. This is not only a mechanical part, but yeah, it was listed in our requirement list. So this is my last slide, because Fraunhofer LBF, the main focus of our institute is the structural durability of mechanical components and systems. I want to talk about some ideas about shock and vibration here. Firstly, the shock test. The first point is you have to get an understanding of how high is your acceleration. Do we talk about 3Gs, 5G, 10, or maybe even 50G of acceleration? And normally you test this in both directions, so in plus and minus, and also in all three directions of freedom. For the vibration tests, here's the big questions. Do we use a standard, or is there a real profile available? The real profile has the advantage that you don't overestimate or over design your system. The standard is normally a quite, or could be a quite heavy test to pass. And yeah. And then the next question is for your vibration profile, do you want to test it in one direction and then in the next test in the other direction? Or do you want to do a multi-axle test? Therefore, you will need a more expensive test rig, but in some cases, it's more realistic. Even for ships, I think, when you have the other degrees of freedom also tested in the same time. And the other question or the other point is, based on the safety issues of such lithium-ion systems, it could be a good advice, or it is a good advice to test first test to make it as a dummy system. That means you have no active cells inside. You have just a weight dummy, a placeholder with the same center of gravity. And when all is done and you are sure that everything will work fine, then you can go with real cells on your test rig. Yeah. So thank you very much. Are there any questions?
Are there any questions online, maybe? No? Okay. One, yes, David.
Hi, thank you so much for the presentation. I was wondering if, as I think you talked a little bit about it, but I didn't actually see anything about electrical insulation and the translation from electrical insulation to mechanical requirements. And I was wondering if you have tackled that issue of actually implementing electrical insulations and the distances. And also there are several standards regarding that topic. So
here in the presentation, I have just touched it briefly in the sense of there has to be a non-conductive material for the cell holder. There are a lot of possibilities which are mentioned on the deliverable, but by the end, we are not in. There's no final decision, and it's not my main field of work. But we have the partners in the consortium who will do this then now.
Okay, thank you so much.
You're welcome.
Is there any other question? No? Okay. Thank you, Eva, for explaining the considerations when integrating the system. Okay, so our next speaker is Bernd Steinhoff from Fraunhofer also. He has been working in the field of plastics technology since 2003 in the German Institute of Polymers, which became plastics division of Fraunhofer LBF in 2012. He obtained his PhD in physical chemistry at the University of Cologne in 1995. And for 2 years, he was a postdoctoral fellow at the German Institute of Polymers. And for 6 years as a software developer with a manufacturer of static and dynamic light scattering instruments followed. In the plastics field, he has been dealing with process control, development of measurement methods, process engineering, material development, and characterization. These included activities on research projects funded by the European Union, the German government, and Fraunhofer internal projects. So Bernd, the floor is yours whenever you're ready.
Okay, good afternoon, ladies and gentlemen. Thank you, Ardin, for the introduction. Now turning onto material considerations. To be more precise, I will focusing on the module casing and not mentioning that much all the other components. Eva just mentioned, for example, the brackets to fasten the cells or containers for the individual cells, and these things. This lecture be taken as an example what has to be considered when dealing with the requirements we have. Now to the requirements, I presume that a thorough understanding of all engineering requirements the material or materials must fulfill, and when this has been obtained and the right material we choose, then this material will be automatically fulfilling in the best way the economical as well as the ecological aspects. Short recap of the we already learned this morning. We will not have a huge housing taking all the cells. We will have a modular approach where the modules, there's smaller packs of in total weight about say 90 kilogram. This energy density basis on a calculation only assuming high power cells. We will have say 24 kilowatt hours. Such packs be stacked in a dedicated department. This approach, on the one hand, we learned this morning is an optimum, is a reasonable approach for the electronical design, and from another perspective, this approach helps also to minimize the effort when defective cells has to be replaced. This will be happen relatively often because in total we will have a quite large number of cells and in the range of some thousand. Turning to the safety requirements, and all packs will be housed in a dedicated unmanned department, and sketched here again. This department must fulfill the highest fire resistance standard. It must be equipped with an appropriate fire extinguishing system. And turning to the material, this means this fire extinguishing systems should be also most effective regarding cooling of heated up modules. And this system bases on water and mist. It might happen that all the packs are exposed to heavy rain, so to say, and then this possibly the marine water is used, or we have nevertheless a salty atmosphere, and together with water we have here a quite corrosive condition also outside of the packs, and the they are just mentioned that we need cooling capabilities to deal with the consequences of a thermal runaway of 1 or 2 cells. The idea is that each pack, such thing, encapsulates the implications of a thermal runaway as much as possible. And this means that the casing must not be absolutely fire safe, but it must be flame retardant. It must retard the energy transfer from the inner to the outside, and we stated here in these international rules. And in addition, the battery pack inside must withstand the electrolyte, the cell chemicals. The thermal runaway might be accompanied with release of the electrolyte into the casing. Then this might also be accompanied by leakage in the cooling system. There we have the usual water glycol recipe, and of course we have a marine atmosphere. Which is more prone to the outside of the housing, but in case of ruptures, or might also be in the inner. Then an additional requirement is that such pack should not be introducing too much additional weight. The goal is to make such pack, say, more or less easily handleable, so that when such a pack has to be replaced, not such heavy lifting tools and etc. are required. And furthermore, regarding recycling, the dismantling of the pack must be easy and safe. No, now to the materials. Materials which are suitable at the first climbs are, of course, the usual construction steel. Then, regarding the marine atmosphere, stainless steel, not all grades, but some of them, for example, this one, that 4401, aluminum, a very well-known construction metal. Then, excuse me, then the usual thermoplastics. Most likely, we will need fiber reinforced grade for propylene, for example, polypropylene glass fiber compounds or polyamide glass fiber compounds. And in principle, we can also think about the well-known fiber reinforced thermosets. Or just going through in the rough glimpse the pros and cons of the different materials. At first, focusing on the metals. When going immediately, so to say, to the average, the materials are quite attractive from the cost point of view, especially this construction steel, very inexpensive material. From the weight, they're absolutely not attractive. Another thing is aluminium, which is not that bad, of course. The strength, of course, optimum. flame retardant. They are not only flame retardant, they are fire safe. Resistance against marine environment in at default setting, no. Some grades of stainless steel, yes. And the other construction steel and so on would require special coatings. Resistance to cell chemicals, more or less the same. I would say this is also a matter of testing. We will have to deal with it at our institute. The stainless steel grade will do well, will do reasonable. Recycling, in principle, recycling paths for metals had been established since those metals have been used. The drawback is that they require quite high energy, and so from the larger view, also generally saving energy, they are not that attractive regarding recycling. Thermoplastics, polyolefins, most likely reinforced grades. Reinforcement can be done by so-called short or long glass fibers. Diameter is the same, about 10 microns, length up to 1 millimeter here and up to 20 millimeters here. The manufacturing of the housing were possible with the economic process, with the injection molding, the mass production process. Just to show how the injection molding does works, you need the mold consisting of 2 shells. When the mold is closed, it is attached here to a screw machine which provides the molten polymer, which is injected into the cavity of the mold, and once the polymer has solidified, the mold opens and you can release the final part. Drawback of the plus of the materials, they can be easily recycled. Also here you don't have to think on the yellow sack with a wild mixture of dirt material, but here we talk on large homogeneous parts, and having such parts, recycling will be quite easy. Drawback of these materials, they are of low, provide not that much strength, they are of low modulus, and furthermore, this modulus decreases in a pronounced way with the temperature. For example, the Young's modulus of a material strongly reinforced with 50% glass fibers at 80 degrees, only 1/7 of the modulus of aluminium. Now to summarize the polymers which were we would think in the first glimpse for making module casing. Very attractive from the cost point of view, very attractive from the weight point of view. Strength not that much. Flame retardants, the natural grades not, but there is a possibility to add special chemicals, flame retardants. This is a field of work of the plastics division of the LBF where I'm with. The flame retardants can be obtained. Very good behavior. Resist against corrosion, atmosphere, marine environment, outstanding. Resistance towards cell chemicals, outstanding with the polyolefins. Indeed, the polyolefins are used as a separator membrane in lithium-ion cells. with polyamide, were a matter of testing, polycarbonate not. Altogether from the polymers tendency, yes, that we will find something which performs, say, good enough towards the cell chemicals, and recycling also quite good. Then the thermosets, that's in lightweight construction material enables the manufacturing of structures which are able to carry very, very high loads. And since about 60 years, these materials have been used for manufacturing of gliders, high-performance sailing boats, and of course the rotor blades of the wind engines. To protect them against marine environment is well known. Resistance against cell chemicals were a matter of testing. I'm not sure with the epoxies. They are not drawback. Two massive drawbacks not suitable for mass production. A lot of manual work, and recycling is still an open topic. They are often also in news journals, or also articles dealing with the problem of recycling of the rotor blades of older wind engines. There's another approach which goes against thermoplastics. It was developed by a former colleague of us at LBF. It utilizes the mass production process, injection molding, but introduces features which we know from the thermosets, where we have reinforcement by continuous fiber layers. The idea is you have the mold of the injection molding machine, and you at the first step you insert a preform of a plastics layer which is reinforced by endless fibers. So, such material is commercially available. Then as the next step, the polymer melt is injected in the usual way, but as a modification here, the polymer contains a foaming agent which starts foaming once the melt has reached the inner of the cavity, and the pressure is low enough. And this means we get a foam sandwich structure with a foam core and fiber reinforced face sheets. This seems to us a very attractive approach for the modules here in the Seabat project. Now, when let's summarize all the material classes again. When going to the last line immediately, the highest amount of plus signs we have here with this sandwich approach, and the other material classes have their one or the other drawback. Now let's conclude this. For the time being, it looks at this thermoplastic sandwich structure will fulfill in the best way the requirements we have for the casing. The material, most likely, despite their strength, will not be the material of choice here at the first glance, but there is a but. Or better saying, however, we have in principle the same, in full analogy, what we have is high power, high energy cells. Lightweight structures need more volume to provide the strength. this means that housing must have thicker walls. For example, in the range of 6 to 10 millimeters, and the housing made of steel, possibly 3 millimeters were enough. And especially when we have to deal with quite large areas which are under a high homogeneous load, the issue of banding and of this might be relevant. And to cope with it, it will be necessary to increase the wall thickness even more. And we might face size and volume restrictions where we have to return to the stronger metals. While steel or metals in general exhibit the highest strength per volume, per volume of the load carrying structure itself, while plastics, on the other hand, exhibits among the materials the highest strength per mass of the load carrying structure itself. And well, we heard all the lectures of today mentioned the hybrid design. Possibly we will end up also with a hybrid design in our case, and even if it turns out that for the casing we don't need a hybrid design, there will be many other cases where it will be very useful to think on a hybrid design, mating metals and polymers. So yeah, that's it from my side. Thank you very much for your attention.
Is there any question? Yes.
Thank you to Fraunhofer in general, Eva, Bernd. It is not a question, is perhaps a clarification of some important points you have mentioned in your presentation, both on the modularity and the materials. Just to say that one of the big gaps in the regulatory framework is the design of the systems on board in terms of compliance with the vibration, acceleration of the ship, because we have in general some broad requirements to cover acceleration and the vibration and the marinization of the components. But these rules are for any system to be installed on board, not specifically for battery or battery packs. So we know where it is not possible to put the batteries, like in the engine room or in the accommodation areas, but we have no requirements where it is possible to do that. And so depending on the position on board, how far from the center of gravity of the ship, also the acceleration can be totally different. We may have ship-specific data for the design. For instance, for some ships, we have seakeeping tests. So we know exactly the acceleration that we will have in a given condition for a specific ship. We may have also additional requirements for, let me say, sort of a crash test in case of naval vessels, or even the consequences of collision or grounding, which have extreme shock or deceleration. But then in terms of compliance, we have to decide together in the project which will be the standard approach, knowing that further assessment will be always possible. And the clear example is in the structure of the cells, where probably the sandwich solution is the winning solution among those that have been selected. But knowing that a hybrid possibility to have the sandwich solution plus some reinforcement made of steel maybe to compensate the racking effect when you have a very high packing of cells, then you may need some additional external support,
yes,
sort of a box or a frame that could take care of these packing and racking effect. So it is something that will be part of the design, but this is just to show how difficult it is to find the right compromise in between all the possible solutions. And again, one size will not fit all, and we have to define what will be the minimum average requirement for the installation, knowing that for specific ship types or operational profile, it will be possible to do something more. So, work in progress.
Thank you very much for this comment. Also to clarify from our side, yes, our thinking at Fraunhofer is also that we need a frame, most likely made of steel to take the boxes, but nevertheless the boxes need to have a strength in itself, simply for the handling purposes. When you remove such a box, it must be self-carrying, and in the inner of that framework, yeah, I think that the boxes will not be touching, that they will be rest on a rail, and yeah, so in principle you will have the situation as you were carrying the boxes during the installation, and so they need an inherent an inherent stiffness, but of course we will need a strong frame for adapting the boxes, which will make sure that they don't swap around during heavy sea and so.
There any other question?
Thank you. This is mostly a curiosity, and it may be silly, and for that I apologize. Are there any solutions, or has anyone considered the possibility to combine the design of the enclosure with or giving it a double function, that is, for example, enclosure and participating in the thermal management? So just a stupid thing, can you have the bottom plate, where is the biggest load, also being a heat sink or even a water cooled heat
yes,
sink?
of course. These are design consideration details we also have in mind, and also during the different work package meetings addressed. Due to the time, I couldn't go, and I couldn't cover all aspects. I haven't said anything about the bracket, all the mechanical components we need in the inner of the pack to clamp, to secure the cells, to secure the battery, the module wide battery management system, and all these things. These are still also still open topics, and we have to work on in course of the work package. The idea of this lecture was to give an idea. We have quite hard requirements addressing a broad range of several aspects. We need strength, low weight, low cost, environmentally friendly, corrosion resistance, and based on cost, you're limited with the materials, and what you have to consider, so to say, just to give an idea. And of course, there is still a lot of open questions we will have to solve until we finally manufacture a module.
Thank you. So, little question. Following your question, could this be maybe more than a solution for the thermal management, for if you put and you use the vessel itself for cooling down, no, the batteries? Could it be a problem if the water is, I don't know, too cold, or I don't know if this have sense? So when batteries are operating, they are warmer and you can use the water for cooling down. But if they are not under operation, could maybe not in this full 100% electric, but in a hybrid system, when you sometimes don't use batteries, could this affect to the battery lifetime, for example? Maybe it's not a question for you, but it just came out.
Yeah, we are not the thermal experts here for the thermal management. But you're talking about the seawater to use, yeah? Maybe, yeah. But for this, I think you need a quite constant temperature. Yeah. But maybe some guys are here for the thermal management and have an idea.
Well, in general, the idea of using a cooling system that is part of the ship, it is valid, of course. I don't consider the direct use of seawater a reliable solution, because we are bringing all the problems of corrosion to the piping system or the plate distribution system on the batteries. So normally we use the seawater and then some heat exchanger from seawater to fresh water in order to control the temperature of the fresh water. And we have hundreds of examples of how fresh water is used for controlling temperature of systems on board. So the thermal management of fresh water is not a problem. It is increasing the complexity of the ship, of course, because then you need the system for the seawater, the heat exchanger, the system for the freshwater cooling and temperature control. It could be the use of chilled water for cooling, or hot water coming from many different sources on board. So it is possible to do that, but then again, it's a compromise in between the complexity, the cost, the maintenance of this additional system, the advantages that we have on the thermal management of the batteries. So feasible, yes, but then in terms of cost-benefit analysis and weight, it is an aspect to be considered. So theoretically feasible, but subject to deeper verification.
Okay, thank you, Bernd. Thank you very much for your presentation. So let's finish this presentation part with some interesting experiences from and synergies from other projects. We have a special guest with us. Karsten Yandura is from our sister project, Current Direct. He is the senior project manager at Blackstone Technology and also the Work Package 3 coordinator for Current Direct project, which consists of development of the waterborne transport battery cell. He obtained his diploma in electrical engineering in 1994 from Technical University of Dresden in Germany, and worked for 15 years as radio frequency and network optimization expert at a mobile communication provider. After that, he worked for 8 years as a systems engineer in a software company, and he's a senior expert in electrical engineering at therein, with focus on formation of lithium-ion cells and Industry 4.0, and also at EBSL with focus on coating of active material using a PVD process. So, Carsten, how is yours? Thank you.
Present the direct project, which is a kind of sister project comparable to Seabat, with the target of a swappable container for a waterborne transport battery. And yes, I'm from the Work Package 3 project manager from Blackstone Technology. And my presentation or my talk today will be twofold. First, I want to introduce you to the current direct project, to the goals, and to the efforts we have done. And in the second part, I want to show something about the ideas of Blackstone Technology, how we will reinvent production of cells. Okay, the current direct project is in response to the call for action to reduce the costs of waterborne transport. And therefore, the idea is to bring a swappable container filled with energy on board of the ship. And we can increase the installed energy in such a containerized system, and all the batteries and all the things around the container needs, battery management system, housing, cooling, fire extension, will be inside this container. It will be a closed system connected directly to the ship. And the second part of this container, we will not only to provide the container, but also the energy as a service platform, which enables the ship operators, the vessel owners, to have a reasonable price to get their energy, so they don't have to buy the container, but they can buy or rent the energy that we're providing inside the system. And doing this, we have 8 strategic objectives. One of them is the innovative waterborne transport cell, which is part of the Blackstone technology. Then the certified battery system, a completely integrated system. There's also certification needed, as well as the certified integration standards. The shore infrastructure is taken into account, and the energy as a service and business and financing model, and also the standard marine battery certification methodology, where we heard from Alessandro, I think, today a good talk about this. And we are just in the middle of such hazard studies to cope with all the things that could happen with the cell, with such a container, when lifting on the ship, when operating on the ship, and charging on the shore. Then the one interesting part is the operational demonstrator. We found or identified a vessel where we can put such a container that we will build on top of this vessel, and will have a half-a-year operation demonstration within a port. And of course, the dissemination and stakeholder management is, as well as I saw for the Seabat project, a very important thing. Coming to the container, we think we use this typical 20 feet container, and we want to equip this container with a capacity of 3 megawatt hours with 1 megawatt peak. And you see here, the cells will be located outside of in the outer side of the container, and in the left side you see all the battery management, firefighting, and all the other systems. So typical, I think, 3 megawatt hour is the intended capacity. And the second part is this energy as a service module, the platform, where we have all the ship comes to the swapping station. It can be ordered a new container filled with a certain amount of energy that is needed for the next journey, and the container will be available, and the swapping will be done in a very short time, because cranes and everything available at the port. We have this grid connection where we can on the shore charge the container again with sustainable energy sources that is available on the shore. And yeah, the operators can do a fleet optimization and pricing optimization. And all this is intended for inland waterways as well as coastal shipping. It's not for the high sea, but it's for inland waterways and coastal. You see here, again, this interface and topology. We have the shore side, where we can connect the container to every national grid standard. We have all the supporting infrastructures there. Then we have this swapping infrastructure at the port. We can swap the container quite quickly. We have also taken into account the human interface. What does the operator has to do during the swapping? What are the considerations for this? And then we have the vessel side, and there we have the question: how many containers can place on board of a vessel? So we can place multiple containers. How will they fit or locked inside the vessel that it's safe during operation? The electrical and machinery interfaces, as well as the idea how to retrofit vessels. An idea I found also in the Seabat, just to bring vessels, for example, they are operating on the Rhine for 80 years and longer. And so if a vessel is in the age of 40 years, you can retrofit with an electrical propulsion, exchange the diesel engine, and then you have a greener mode of transport, even for those quite old ships. And the current direct project started also in 2021. We have 13 partners from 9 countries and 1 demonstration site. And we have here our advisory reports are about companies that are interested in this technology. And I come from Blackstone Resources or Blackstone Technology, situated in the middle of Saxony, Germany, in the eastern part of Germany. And so we go forward. Blackstone Technology, what do we want to do within this project? Our goal is a new process, introduce new process into manufacturing of batteries. And we think that printing is one of the best ways to do this. What's our motivation for this? We want to have higher energy density. As we see, we don't have enough space on a ship. We have to put more energy into the cell. We want to be flexible in formats. We want to decrease production costs. At the moment, we have quite high production costs for cells. And we want to improve the environmental impact of production and of the product. So, and therefore we invented the so-called Blackstone single-layer technology based on 3D printing. And this now enables us with a really high flexibility in case of formats. If you know all the cell plants for automotive, they have just one format for the cell. And that's it. And you have to put millions of euros to change the size or the format of the cell. we want to have low energy consumption and low production cost. We don't use any toxic solvents, as we saw before in this cell manufacturing chain. There was this solvent recovery from this NMP, and we have a completely water-based solution. And this enables us to in resource-saving battery recycling. Here we see our factory, or part of our factory. And the motivation or the vision is that we want to make battery cells like semiconductors. Today, you can go to a semiconductor manufacturer and say, okay, I have this chip with this design. And within Foundry, you can do, okay, if you have thousands of these pieces, we can make this for you. And it's the same what we want to achieve with a single machine park. We want to print the cells in their format as the customer needed it. How do we want to do this? Yeah, the Blackstone Group is divided in Blackstone Technology and battery metals and precious metals. So it started all with this mining. The Blackstone Resources had an asset trading company. They had assets on mining companies, and then they find out that they have all materials available that were needed for production of lithium-ion batteries. And that's the idea, to close the value chain and just to go from mining to active material to cell, and at the end, pack and modules and recycling. And in the middle, the cell, this is the step we are now focusing. Here our short timeline about this. Founded in 1918, quite young company. And we had the first sample of a battery cell with 3D printed electrodes in 2020. Here we see in the middle the cell we are now targeting for the current direct project, which is a pouch cell, indeed. And we are just working on the first B samples for this. Then we show the further development, the first proof of concept of a 3D printed all solid state battery for this. And yeah, we will start the production of those in next year. Yeah, again, our benefits for this. We have this solid state batteries we want to print with this unparalleled flexibility. And we have conflict-free materials because we know where our resource materials came from. And we can have a cost-efficient scaling up for the production because we're using standard machines we will develop now. And you see here part of our printing machine. We have here, we are just printing active materials on foil, on copper and aluminum. And these all will be slitted and will be assembled to cells. And this is one of our main processes we have. The second interesting process is the generation of this paste, which looks like this black one, which is comparable to Nutella from the thickness, from viscosity, and you have to handle with this paste. And we use really only 40% of solvent, of water for this. And it's really viscose and thick, and you have to handle it properly. See here again, this materials, the paste, the print line we installed yet, and our product. And from these, we are planning with about 12,000 cells that will be integrated into such a container. And yeah, based on our own materials, we will use the printing technology and producing lithium-ion electrodes, cells, solid-state batteries, and solid-state electrolyte. How will this work? It's quite a known technology, screen printing. Screen printing done in multiple layers, and therefore we can build three-dimensional structures on the electrode. And this enables us to print multi-layer batteries, bipolar batteries, where we have anode and cathode layer on top. And so we can build, for example, 60-volt batteries or a defined thing. We can embed printed electronics inside the battery, which is quite interesting for sensors like temperature or current. And we also looking into manufacturing the battery structures, so completely printing the cell enclosures. And at the end, we want to focus with to print complete cells. Yeah, this is our printing technology with this high viscosity paste, with aqueous solvent, and at the end, with 20% more energy density compared to the typical production of electrodes. We've done some evaluations of this technology, which is going into thick layer coating. You see here the discharge capacity in milliamp hours per square centimeter. And this one is our Blackstone comparison compared to literature. Our Blackstone curve is this. And so we are quite good, or compared to the existing literature for high density or high energy cells in this case. And this 3D printing allows us to print three-dimensional structures, and this can adjust the C rate or the usable C rate for the battery. And you can imagine you can print such structures with this screen printing on your electrode. This gives a shorter diffusion path of the lithium ions into the deeper parts of the electrode. And you see from some comparisons from our research institutes that with this 180 hex print, you see that here the C rate is much more better compared to a normal coated anode or cathode. When you have these structures inside, and today there are experiments with laser ablation of these cathodes or mechanical structuring of the cathodes, and that we can do with one step, with one printing step, which is quite innovative and new. And using this technique, we all have the chance to have different formats without changing the complete machinery. So we have to change only one part for this. We can print different formats usable for cycles and motorcycles, for cars, electrobuses, computers, and yeah, we are really flexible in the dimension we want to do. And the way goes further on, as you heard about these solid state batteries that have a higher energy density. We can build larger batteries with them, and we have longer drive-ins, light distances compared to today going from 600 kilometers to more than 1,000 kilometers per charge. And this one is our first printed battery with this technology readiness level of 2 to 3. And we started just a project that comes up to technology readiness level 7, that we can have this printed battery, solid state battery available at our plant. There you see here the small LED is lightning, and you can use a scissor and can cut through the battery, and the LED will lighting further on. It's quite impressive to see this. And this is the way it should work. So we want to print a composite electrode, we want to print the separator, we want to print the housing, and then going further to the metal anode printing of the current collectors, and again the housing. And so we have a completely printed cell in multiple steps. And the way is looking for sodium instead of lithium for this thing. Of course, sodium is much more higher in accuracies than lithium, and its cost only a fraction of compared to lithium. And if you're just looking to the lithium prices the last days or last year, the volatility, so we have the chance to get a better product for this. And therefore, we started this 3D print pad project, 3D print pad. And the consortium leader for this is Blackstone Technology. And yeah, it's the very new, very interesting thing we're just developing. Okay, what are our customers? And you see here from EVs, e-buses, aerospace, electrical storage systems, very interesting, industrial vehicles, but also current direct marine applications, which is our primary first customer for our technology. And yep, that's something we just achieved from the German Innovation Award, which is quite good for us, a good position in the market. And with this, I want to close my talk with a picture of our company and back to current direct, where we want to place charging stations around Europe to help to improve the inland waterway traffic. Thank you for audience.
Okay, is there any questions or comments?
Being part of the current direct project and now having seen the outcome of Seabat thus far, what was for you the most important takeaway of the workshop today that you see compatible with current direct?
I think there are many things we are looking in the same way, just with all these security levels, how to analyze these things, to look into the batteries we are using. We don't focusing on this hybrid effect. We just want to have one cell type for this, but it's quite comparable projects looking for electrification. And I think we can have a good cooperation and we can learn from each other, in this case, from exchanging information, exchanging data from this. So it was quite a brilliant, a good experience for me.
Questions? Okay, thank you, Carsten.
Thank you.
Let's have a break, 45. So we can enjoy the poster session as well and see what are doing our PhD students and other partners from the project. Okay, and we will meet here again at 2:20, more or less. Yes. Okay. We are not on a schedule at all. Okay, thank you. So, in the hall.
The day you left me and went away, well, I haven't seen the sunshine since that day. Now I'm alone and I'm so blue, and everywhere I turn there's memories of you. I can't shake you. I can't shake you. I can't shake you. No matter how I try. I feel numb and I feel tired, and I ache all over on the inside. I'm so lost and I'm confused. Everywhere I turn, there's memories of you. I can't shake you. I can't shake you. Lord, I can't shake you. No matter how I try. I try to run, I try to hide. Okay, can you hear me? Yes. Okay, so
let's begin with the end of the workshop. Today we have seen that the maritime sector is facing a lot of challenges, and we will try to provide the solutions. No, we know that the electrification of this sector is one of the key solutions, but in order to electrify the vessels, we have to also consider that the costs of the batteries must be reduced. We have to work also in the integration of the whole battery system into the vessel. During the day, we saw in different presentations what are the market needs and how is the regulatory framework in this sense. We also talked about the requirements that the battery system must fulfill, and also what are the most suitable converters for these applications, and how to do an optimal design or a cost assessment. What is clear is that we have to continue our research on this field, and we want to encourage students and also researchers to continue pushing this field further in order to make this sector more efficient, more cost effective, and also more environmentally friendly, of course. And we would like to thank you, all of you, participants, speakers, and people also from the organization, because without your inputs, ideas, and discussion, this workshop wouldn't have been possible. So thank you very much. And well, we want to finish by mentioning that, as Fabio said in the morning, the next academic workshop will be held at Polito next year, in June 2023. So we hope we will see there again. And of course, you are all invited to attend the workshop. And well, we don't know if there are some questions or something else that you want to comment, or people online, no? Okay. We would like also to thank you, those who are attending online. We hope you enjoyed the day, the most part of the day. And well, we okay. So if you want, we will continue. We will continue with the tour from our labs and facilities. We will go then also to Ikerland's facilities, and we will join also the social event after that. Okay, thank you very much. Okay, thank you. Yes.